Over 200 million miles away from Earth, Osiris-Rex is preparing for NASA's most ambitious sample return since the Apollo program. After months of detailed analysis of Bennu's terrain, the team selected the Nightingale crater as the sample site for the mission. Osiris-Rex will need to carefully dodge rocky hazards as it descends to a space no larger than a few parking spots. The spacecraft has mapped the terrain in high resolution, capturing a stunning catalog of images across Bennu's rough surface. And now, we are ready to target Site Nightingale for the touch-and-go sampling event.
In the dark voids of the solar system, drifting in between the familiar planets and their families of moons, are the asteroids. There may be 1 million, perhaps 2 million of these cold, dark rocks. But these small worlds are anything but dull. In fact, some of them are time capsules from the very beginning of the solar system, unaltered for billions of years. And in fact, the clues to how everything around us began, from the formation of the planets to the beginning of life itself, may be locked up in these asteroids. And tonight, a spacecraft from Earth is going to touch one, bring back a sample, and prepare the long journey back to Earth where we can analyze it. Welcome, everyone. I'm Michelle Fowler from NASA's Goddard Space Flight Center, and thank you for joining us. I'm speaking to you live from the Mission Support Area at the Lockheed Martin Space in Littleton, Colorado. As you can see, I'm struggling with my mask here a little bit. We're here to follow the sample collection for NASA's Osiris-Rex mission. This is an operation referred to appropriately as TAG. Now, remember that this is a historic event. Today's endeavor will be the first time the space agency has ever touched the surface of an asteroid, collecting a sample of this pristine ancient material, a scientific treasure far more precious than gold. Joining me throughout the show will be the principal investigator of the Osiris-Rex mission, Dante Loretta. Welcome, Dante.
Thank you, Michelle. It's really great to be here today. I'm a professor at the University of Arizona, and I have the honor and the privilege of leading this amazing mission for NASA and really for the world.
It's pretty amazing. So now the main event is happening in about an hour. And this is called TAG. Can you explain to us a bit why it's called TAG?
Yeah, today we're tagging an asteroid, and TAG is an acronym that describes our sample collection strategy. We're going to send the spacecraft down for a short duration contact with the asteroid surface, anywhere between 5 and maybe as long as 15 seconds. So we call it a touch and go, or tag an asteroid.
It actually is almost sort of like a quick touch, a tag. It's a very good way of putting it.
Exactly.
Yeah, absolutely. So there's lots of asteroids out there. We talked about the fact that there are a couple million. So why have we selected this particular one to sample?
Yeah, the target of our mission is called Asteroid Bennu. And when we were designing the mission, we had to consider both engineering constraints and, of course, our science objectives. And when we looked at the capabilities of our spacecraft, we knew we needed to go what was called a near-Earth asteroid. So we were basically looking at its orbital properties and its location within the solar system. We needed an object whose orbit was pretty similar to the Earth so that we could launch off of our planet, rendezvous and spend some time at the asteroid, and then leave and bring this precious scientific cargo back to Earth.
Absolutely.
And then from the science perspective, we're really answering some fundamental questions. Why are we here? Why is Earth a habitable planet? How did the origin of life occur? So we wanted an asteroid that we thought was rich in water, that may have brought the oceans to our planet, and also rich in carbon. We're looking for the organic seeds of life that may have led to evolution as we know it today.
And this is really an amazing point, our connection to these asteroids. So what you're saying is that some of the organic compounds in my body, some of the water in my body right now, may originally have come from asteroids.
Almost certainly. The Earth was accreted from these asteroids. Bennu is a remnant that survived that process, but it's the geologic history of our solar system that's locked inside this body.
Absolutely. Now, there are many other asteroids like Bennu in the solar system, and of course there are some that are even larger. Over the last decades, we believe we have found nearly all of the potentially dangerous ones. Oh, we'll pause.
OREX natural feature tracking system has resumed processing. Position uncertainty is 1.6 meters.
Excellent. So getting back to my point, we know there are others out there that we have not yet detected. In fact, just this past August, a truck-sized asteroid missed the Earth by less than 2,000 miles, and nobody even knew it was headed our way until it already passed us by. So for our survival, it's essential that we understand what's out there in our environment in space. And this is one of the main objectives of the Osiris-Rex mission. we'd like to go out and meet Bennu before something like Bennu comes and meets all of us. So Dante, what can you tell us about this idea of planetary defense?
So as a result of Bennu having this optimal orbit for sample return, it also is what we call a potentially hazardous asteroid. Because its orbit literally does cross the orbit of the Earth, and there's a probability about 150 years in the future that Bennu may in fact impact our planet, creating a natural disaster. So Osiris-Rex is really trying to study Bennu's orbit very precisely. We know that sunlight actually influences the trajectory of these small asteroids, and we're studying that phenomena, how it interacts with the asteroid surface, and ultimately how it's going to allow us to assess the impact risk that Bennu poses to the Earth.
Absolutely. So the idea of planetary defense isn't just an intellectual exercise. It's something that NASA takes very seriously. A little later in the broadcast, we're going to talk with some people more about protecting the planet from surprise visitors from space. So back to Bennu. We have a lot of exciting stuff to share with you about this tag operation, from how it works to why this overall mission matters so much. And you can be part of this too by joining us on our social media platforms. I'd like to introduce James Traley at our social media desk. James.
Yeah, thanks, Michelle. My name is James Traley, and I'm a producer at NASA Goddard Space Flight Center. And today, I'm joining you on social media to share the excitement of the Osiris-Rex mission and this incredible sample collection event at Asteroid Bennu. To join us today, you can use the hashtag #BennuAndBack on Instagram, Facebook, and Twitter to join the conversation and share the excitement with all of us here. You can also follow the mission's Twitter account at Osiris-Rex for live updates as we make our tag attempt. We actually have a poll going on at this Twitter right now, where we're asking you, how much sample do you think Osiris-Rex will pick up at Bennu today? I'll check back in with you in a little bit for the results, but for now, back to you, Michelle.
Thanks, James. Okay, so right behind me is the MSA, the Mission Support Area for Osiris-Rex. And today it is filled with very excited people, the scientists, engineers, and technical specialists who've worked on this mission, in some cases, for more than a decade. So back there is Gary Napier from Lockheed Martin. He's right in the middle of it all. So Gary, what's the feeling in the room?
Michelle, like you said, I am just right behind you, about 20 feet. We're here in the larger Lockheed Martin Mission Support Area, where we're operating 6 of NASA's spacecraft around the solar system, 4 of them at Mars, 1 of them at Jupiter, and this one right here, Osiris-Rex. We're going to take you into the operations center here at Osiris-Rex. This is where the flight team is right now. The controllers are already on board. We've heard some good call-outs right now. And in a little while, we're going to come in here and talk to some of them and see how things are going. It's looking really good right now. Back to you, Michelle.
Thanks, Gary. So I think right now we have to acknowledge something, that this is a bit of an unusual broadcast. We're dealing with some pretty big challenges tonight because we're doing this all in the midst of a pandemic. So you'll notice that I'm wearing a mask. I've certainly never hosted an event wearing a mask before. Forgive me if I struggled with it a little bit tonight, and make sure that it's in the right position. And when we interview people, you'll notice that we'll be standing farther away than normal. And also, I'm going to stay right here. Normally I might be back in the mission support area, but I'm not allowed to go back there. I'm isolated from them. So it's amazing that with the incredible operation going on at Bennu tonight, and the people all around me who've been working on this for years to make this a success, we still have to deal with the challenges of COVID-19. And so, tonight our attention is going to be on this wonderful event, actually sampling an asteroid. And, that's incredibly adventurous, it's very happy, but we're going to remember to actually take care of each other. We can't forget that. So please bear with us today as we are working with our masks and trying to do this the best way we can. Okay, so Dante, give us a chance now, give us sort of an idea about how the engineers back there are actually flying Osiris-Rex.
So it's important to understand that the spacecraft is actually literally on the other side of the solar system, over 200 million miles away from the Earth. So any signal that we were to transmit here would take over 18.5 minutes to reach the spacecraft. So when we get these signals back, we're actually seeing things that happened in the past at the asteroid. As a result, we have to have a very smart spacecraft. It has to make its own guidance calculations and make its own decisions. And in fact, instead of getting high data back, we're only getting a very low data rate, what we call breadcrumbs, just key pieces of information from the spacecraft that tell us when key events have taken place in the tag sequence.
Osiris has processed its next image. Position uncertainty is 0.9 meters.
So that's an example of the kind of information that we're getting back from the spacecraft. It's got its onboard natural feature tracking system, which we're going to hear a lot more about today.
Absolutely, yeah. All right, so I guess after that, we are dealing with, actually the tag event itself, but I understand that we're not going to be able to see images tonight in real time, that we have to wait a while. Why is that?
The images take a lot of data to bring back to the bring back from the spacecraft to the Earth. And since we're on that low data rate, what we're using today is this real-time simulation that we've put together. So what we're seeing here, and we'll be referring to this throughout the broadcast tonight, this isn't any kind of real information from outer space. This is what we expect the spacecraft to be doing. So it'll let us know when key events are programmed to take place on the spacecraft and to be received back on Earth. There may be some lags in communication, but this is going to really help us visualize what's actually happening at Asteroid Bennu.
So when will we expect those first images?
So everything's going to play out at this very low data rate through most of the broadcast today, and then the spacecraft has to back away from the asteroid surface, it has to cool off, it has to get back on its solar arrays, and then it's going to turn that high-gain antenna to the Earth this evening, and we expect images to be coming in overnight, and we hope to have some great information for everybody by tomorrow.
I'm really looking forward to those images. People around the world are. So at this point, the spacecraft has left its home orbit and it's on its way to the sample site. And every minute now, we're drawing near to that moment when Osiris-Rex touches the surface of Bennu. So while we're waiting, let's check in with James at our social media desk.
Yeah, thanks, Michelle. So a few days ago, we actually hosted a Reddit AMA with a few of our scientists and got a lot of fantastic questions. We wanted to recap a couple of them for you right now. So our first question asks, how is it possible to map such a tiny speckle in the sky? Do you have any detailed images that you can share? Do you really see the landing site, or is it all based on measurements of some weird properties and calculations? So yes, our first observation of Bennu actually came from right here on Earth, from the Arecibo Observatory in Puerto Rico. This huge radio telescope gave us a basic understanding of the rough shape of Bennu, this kind of strange top-like shape that you see right here. As Osiris-Rex was actually out in space, and began making its approach closer and closer to the asteroid, it used its suite of onboard camera instruments to actually image the surface in increasing detail. Bennu grew in detail from just a few tiny pixels on our screen to this super high resolution world that you see right here, littered with giant rugged boulders. Another question from Reddit is asking us, let's see here as it loads in, yes. So would it have been feasible to have a robotic arm pick up a rock? Would a single rock have been better than 100 tiny grains of sand or ice? So the team had originally designed Osiris-Rex to sample on a nice, flat, sandy-like surface. But as you just saw, Bennu is not at all like that. It's super rugged and filled with giant boulders. So the team had to work with what we had designed for, which was that flat, sandy surface. If we were to try to sample on a rock, that actually presents a number of challenges of its own. For example, if we were to pick up a rock, it might actually just crumble away, and we wouldn't actually get a sample out of it. Also, some of these rocks might actually be a bit too stuck to the surface. And if we were to try to pry those loose, they might not actually budge, and we wouldn't actually even get a sample. So, these are all things that the team has to consider when designing something that's going to be operating millions upon millions of miles away from us here on Earth. So for now, back to you, Michelle.
Thanks, James. We'll be back to you more for later. Okay, now, I have been a Star Wars fan nearly all my life, and in one movie, Darth Vader said, rather famously, that asteroids do not concern me. But that is certainly not true for us this evening. We are all about asteroids here at the Mission Support Area in Littleton, Colorado. And we are bringing you live coverage of our attempt to collect a sample from the asteroid Bennu. Now, Osiris-Rex is a one-of-a-kind spacecraft with an extraordinary team of engineers and scientists charting unexplored places. It was launched on September 8th, 2016. The vehicle has traveled over 2.2 billion miles on a complex route to reach Bennu. It's scheduled to deliver its precious cargo back to Earth in 2023. So now let's take a closer look at Osiris-Rex.
Over 200 million miles away from Earth, NASA's Osiris-Rex spacecraft is preparing for an ambitious sample collection attempt at asteroid Bennu. Before it makes its approach to the rocky surface, let's take a look back at some of the incredible firsts for this mission, which almost seem like something out of a Hollywood movie. This is the first asteroid sample return mission for NASA, and it could be the largest return from space since the Apollo astronauts brought moon samples back to Earth. While getting set to grab a sample, Osiris-Rex has set not one, but 2 Guinness World Records. Its first for the smallest ever body orbited, and its second for the closest orbit of a spacecraft. This tight orbit has brought the spacecraft so close to Bennu that Osiris-Rex's onboard cameras and laser altimeter have been able to image and characterize the asteroid's surface and shape better than Earth, our own moon, or any other celestial body. Osiris-Rex has imaged Bennu down to 5 cm per pixel resolution, providing us with an unprecedented view into this rocky and boulder-filled world. With 28 onboard thrusters, Osiris-Rex is one of the most maneuverable spacecrafts. This allows it to carefully and precisely descend to a spot on Bennu that is no larger than a few parking spaces. There have certainly been some unexpected twists along the way. However, Osiris-Rex has capitalized on these moments. Right after arriving at the asteroid, Osiris-Rex imaged rocky ejecta that has been bursting off Bennu. This is the first time we have been able to observe the entire life cycle of a natural satellite ejecting off an object, entering into orbit, and returning back to the surface. Because of Bennu's extremely rocky surface, the team needed to adapt the spacecraft's navigation method to an optical approach known as natural feature tracking, or NFT. This is the first time this approach has been used in space, and it will allow Osiris-Rex to steer itself down to collect a sample from Bennu. And now, Osiris-Rex is looking to set another first for NASA. Successfully collect a sample of an asteroid and deliver it to Earth by 2023.
Welcome back. If you're just joining us, I'm Michelle Fowler from NASA's Goddard Space Flight Center, and with me is Dante Loretta from the University of Arizona. And you are here with us on a historic evening. It will be NASA's first sample return from an asteroid, the attempt to actually sample the asteroid Bennu. The spacecraft Osiris-Rex is descending toward Bennu right now to take a sample and return it back to Earth. So Dante, let's talk more about this real-time simulation that we're looking at.
Yeah, it's been an exciting day already, Michelle. We're well over 3 hours into the tag sequence, which is the pre-programmed set of commands that are already on the spacecraft. Earlier, we departed our orbit around the asteroid, so we're flying over the sunlit side of the asteroid, taking images for the onboard guidance system called natural feature tracking. A couple other key events that have taken place already is the spacecraft has deployed its robotic TAG-SAM sampling arm, so the arm is ready, in position to collect that sample. And we've turned on and started collecting science data from one of our science instruments, the Otis thermal emission spectrometer. The spacecraft has already moved into its second natural feature tracking attitude and is getting onboard positional updates as we speak. And I can tell you everything is going exactly according to plan right now. It looks really good.
Oh, it's been an exciting day. So Osiris-Rex has traveled more than 2.5 years as it navigated its way to this delicate orbit around Bennu. And once there, it began mapping the surface, one of the many tasks it and the engineering team have been conducting since it arrived. And there have been some challenges and surprises too, correct?
Absolutely. I can tell you already the science return from Osiris-Rex has been phenomenal and rewritten a lot of things about what we know about asteroids. I'm going to talk really about 3 of some of the most interesting results for me. First off, we learned literally about 1 week after getting into orbit that Bennu is what we call an active asteroid. It is ejecting particles from its surface. These particles are coming off at relatively low velocities for the most part. They're actually going into orbit, spiraling around the asteroid, providing some excellent science, allowing us to map out the gravity field of this small body at an unprecedented detail, way beyond what we expected to do. The other thing that we saw right away as we were approaching is that there was some generally dark black surface as expected, but there were these really bright boulders that were shining like beacons to us. And as we trained our science instruments on there and characterized their mineralogy, we were actually able to link them to another asteroid called Vesta, one of the largest asteroids in the solar system, and actually the target of NASA's Dawn spacecraft, which did a phenomenal job characterizing this target. And this just shows you that these asteroids are exchanging pieces back and forth as they collide into each other and shoot their particles off into space.
OREX has processed its next image. Position uncertainty is 0.6 meters.
Wow. And I would say, back to the science, the final result that really is important from this mission is we did expect this asteroid to look sandy and beach-like. And that was based on the thermal properties as determined from telescopic observations from Earth. And we got there, and we used the Otis and our OVIR spectrometer to map and produce a thermal inertia characterization of the entire surface. And everything turned itself upside down based on our models. The areas that we thought would be beach-like based on thermal properties turned out to be the largest boulders on the asteroid's surface. And the more fine-grained regions turned out to have what we call this higher thermal inertia, completely opposite of everything we expected, propagating a lot of great science as a result.
And so when you mentioned that there are these bright rocks from Vesta, does that means that Bennu was once in the asteroid belt between Mars and Jupiter?
That's right. Bennu is currently a near-Earth asteroid, but it's a recent wanderer into the inner solar system. We actually think it's fragments of a much larger asteroid that was catastrophically disrupted maybe 1 billion years ago.
Wow, that is so cool. Thank you so much. Okay, now as challenging as it is actually getting to Bennu, capturing a sample of the asteroid is something else entirely. And the team needed to develop this remarkable system. The Osiris-Rex mission has been in development for almost 20 years, with the engineers and scientists developing new technologies and strategies to accomplish something that's honestly never been done before. And this is particularly challenging because Bennu has such a weak gravity field. So when you think about going into orbit around something, how do you orbit something where the gravity can't grab you and actually push you into orbit? It's all about flying the spacecraft. It's also very difficult to take a sample in a very low gravity environment. So thankfully, we have the mastermind behind the device that's going to take the sample tonight, Lockheed Martin's Bo Bierhaus. Welcome, Bo.
Thank you, Michelle. It's great to be here.
Okay, so let's talk a bit about why working in this low gravity environment makes it tough to get a sample, because you might think sort of at first you could just take like a robotic claw or a robotic arm and scoop something up, but that's not going to work in these conditions.
That's exactly right. The microgravity of Bennu provides a challenge of sampling that we don't normally face on Earth. You can imagine trying to use a shovel or a scoop on Earth, and the ground pushes against you, but the gravity keeps you on the ground. On Bennu, the surface gravity is thousands of times lower than on Earth, so if you pushed a shovel or a scoop into the ground, you'd push yourself right off the surface. So we had to come up with a technique that worked with this very low gravity. We also had the challenge of uncertainty of the mechanical properties of the surface. And both of those things made landing a challenge. We wouldn't know how to grapple particularly well in this material. So we had to come up with a technique that worked in the microgravity environment and that could work in this tag architecture, this touch-and-go architecture of just a few seconds long.
Now, I understand you have brought some models with you, both of the spacecraft and of the instrument that will be taking the samples. So show us what you've got here.
That's exactly right. So this is a scale model of the spacecraft. The arm is extended in the sampling position. Partway down the arm, you can see 3 gas bottles. We'll use one of them today. This has high pressure nitrogen gas, which passes down the arm into the TAGSAM head itself. And here I have actually a full-scale TAGSAM. It's actually a device that we used for collection testing on Earth. The gas comes down. I don't have the tubing here to show you, but the gas comes down to the center of the TAGSAM, is split into 2, and passes underneath the head. There is now a high-pressure bubble of gas underneath the head that is mobilizing material, much like wind blows dirt on a dusty day on the Earth. And we're surrounded by the vacuum of space. So the gas there's a high-pressure gas underneath TAGSAM, and it will escape into the low-pressure environment of the vacuum of space surrounding it. And it does so through this screen around the entire perimeter of the TAGSAM head itself. But while the gas can escape, the screen traps the material safely inside.
It's one of these sort of brilliant things about engineering for space is to have things that are really, really rigorously built and they can't break easily. And so there aren't even any moving parts here, and you're using the vacuum of space itself to provide the pressure to collect the sample.
That's exactly right. When we were first designing this device many years ago, we were thinking we wanted to keep it as simple and as robust and as foolproof as possible. We didn't want any mechanisms, we didn't want any electrical devices. The entire collection is driven by the dynamics of the gas itself. So once the gas is released from the bottle and travels down the arm, the gas does all the work.
That's so cool. So what size particles are we talking about collecting here?
Well, TAGSAM is designed to collect 2-centimeter particles, and I have some examples here to show you. So this is a 2-centimeter sphere. It's about the same diameter as a nickel. But of course, most geologic materials aren't actually perfect spheres. Most geologic materials are irregularly shaped.
Osiris has processed its next image. Position uncertainty is 0.5 meters.
Oh, that is fantastic. Excellent. So we're going where we need to go to get this material. So most geologic material is irregularly shaped. So this rock is actually about 4 centimeters long in its longest dimension, but we were still able to collect this in a test on Earth. And that's because even though it's 4 centimeters in this dimension, you can see that it's much less than 2 centimeters in that dimension, or even 2 centimeters in the other dimension. So while we're limited in one direction for 2 centimeters, as long as the other 2 directions are less, we can actually collect much larger particles into the tag SAM head itself.
Well, excellent. So I understand we have some animations queued up to give us a sense of what's going to happen on the asteroid tonight.
Sure thing. So what you're seeing is the spacecraft descending at a leisurely 10 centimeters per second to the surface, 15 times slower than walking speed. It contacts, the spacecraft senses contact and fires the gas. The gas mobilizes material underneath the tag SAM head. That gas escapes into the vacuum of space through the perimeter, and materials collected inside the tag SAM head. The spacecraft fires its thrusters and backs safely away from the surface of the asteroid.
Well, thank you for the tutorial, Bo. I mean, clearly the science community is going to be very excited to study whatever tag SAM collects. So thank you so much.
Thank you. It's wonderful to be here.
Okay, well, speaking of all the important the thing that's happening in less than an hour, right now, before we get any later, it would be a good time for us to get a tour of the Nerve Center here at Lockheed Martin Space in Littleton, Colorado. Right behind me is the Mission Support Area, or MSA, and that's where Osiris-Rex team members are keeping an eye on the spacecraft right now. So let's send it over to Gary. What's going on, Gary?
So as I showed you earlier, we're just around the corner from you. This is the heart of the tag operations, and we thought this would actually be a really good time to kind of check in with the team, see how things are going, and the best person to do that is joining me, and this is Sandy Friend. She's the Osiris-Rex operations manager here at Lockheed Martin. So Sandy, thanks for joining us. How's the team doing?
Oh, the team is great. We've been here on console since 6 o'clock this morning, setting the final commands, getting ready for tag.
Really cool. I know there's like 40 people on your overall flight team, but it seems like there's about 20 of them here right now. Maybe kind of give us a little idea of who some of these folks are and what they're doing.
Yeah, absolutely. So this is the amazing OREX team. You can see all of our subsystems here on console, monitoring their telemetry. Like you mentioned, we can't have everybody in here. We do have many team members supporting from other conference rooms in the building, and some even from home. So let's talk about a couple of the positions we have in the room. In the back corner over there is Dale Howe. Dale is our tag phase lead. You've been hearing his voice calling out events as they complete on board the spacecraft. Here in the center area, we have Curtis Miller. Curtis is our NFT lead. He is watching natural feature tracking, and that is how we are navigating to the surface of Bennu today. So he is watching how NFT is performing, how many features we're matching, and how that system is working.
So I know natural feature tracking, like you're saying, is kind of keeping an eye on telling us where we're going, and I know we're going to get into that a little bit later in the show. But also it's important just to stay in communications with the spacecraft. So what about comms?
Yeah, absolutely. So right behind me here is Sierra Gonzalez. She's our real-time operator, or our ACE. She is working with our Deep Space Network partners. Currently we're on a station in Goldstone and in Canberra, making sure we maintain our comm link. And our comm link is only 40 bits per second, so we're just bringing down that key information, but Sierra's here to make sure we keep that link going and our station operators informed. And right next to her is Estelle Church, and Estelle is our systems coordinator for this event. She's built all the command products that are executing. She's keeping an eye on how everything is progressing on board the spacecraft, talking to all of our subsystems here in the room, and making sure things are going just as planned.
Very good. I know you yourself have actually been on this project for quite a while, even back to development. I mean, how are you feeling tonight?
No, actually, I'm excited. I feel like we've done everything we can to make this successful, and I've been on this mission for 7 years, so I've watched it go from a spacecraft on paper to being built in our high bay to launch and everything here, and yeah, I'm excited. My kids were excited this morning, and we are ready.
Right on. That's so fantastic. So we're going to let you guys get back to it. I know we don't want to interrupt too much. Sandy, thank you so much for joining us. And I know that folks around the world are paying attention to this right now. We're seeing a ton of social media coming in. So let's go over to James on the social media desk and see what some of those conversations are about.
Yeah, thanks, Gary. It's awesome to see the team over there in the MSA. You can really feel the energy in the room, especially after every call out from Dale. And right on cue.
OREX is slewing to the tag attitude, the third and final natural feature tracking attitude.
All right, so we're inching ever so closer down to the surface of Bennu. But today we also want to hear from you. So you can check in on live updates at our Twitter account at Osiris-Rex, or using that hashtag to Bennu and back across social media to get in on the conversation. In the meantime, a question I had when I first started covering the mission is, how do you even begin to prepare for a mission of this scale? I mean, when I first heard about Osiris-Rex, it really seemed like something out of a big budget movie. But this is a reality. We're actually going to be trying to sample on an asteroid. To put things into perspective for you, Bennu is about the size of the Empire State Building. That's really small for an object and makes it exceptionally challenging for us to orbit something with such a weak gravity field. And that sample site we're going for today, Nightingale, it's just a few meters in width, which is about the size of a few parking spaces. So just take a step back for a second and put yourself in the shoes of some of those engineers on this mission. And imagine trying to park a spacecraft on an asteroid 200 million miles away in a space no larger than a few parking spots. As if parallel parking on an asteroid isn't hard enough, imagine also trying to dodge hazards like rocky boulders and all kinds of things as you're making your descent down to collect a sample. And on top of that, the team has actually programmed the spacecraft to steer itself down to the surface. It's truly incredible, this mission, and all the foresight that went into it. It really blows my mind. We actually have a couple questions coming in from Twitter, and a lot of people are actually asking about our fuel usage for the mission. This one question is asking, how does the craft have enough fuel to return back to Earth from the asteroid? So we're looking to bring that sample back in 2023, and Osiris-Rex's thrusters are actually powered by hydrazine, which is stored in a container on the spacecraft. We're tapping into a little bit of that fuel today, on the order of maybe tens of grams, not a lot, because as you remember, Bennu has this microgravity environment, and it just requires a little bit of thrust to kick us in the right direction to collect a sample. That return trip back to Earth, that's a bit of a different story. We're going to be using a lot more fuel for that. But don't worry, the team has thought way ahead and has packed more than enough fuel to get us back here safely in 2023. But there's a lot more to come, and I'll check back in with you in just a minute. Back to you, Michelle.
Thank you, James. Okay, so let's take a quick look at the simulation to see where we are. As you notice with the simulation, the spacecraft has its arm extended now and is on a slow path toward the surface. So as we get closer to the moment of contact, the drama starts to happen in slow motion. And this is to maximize precision and minimize unintentional surprises. So, speaking of surprises, there is one big aspect of the Osiris-Rex mission that's all about preparing for the unexpected. And joining us to discuss this is NASA Planetary Science Division Director, Lori Glaze. Now, Lori, you have kind of a dramatic specialty and a responsibility that comes with your position at NASA. You actually worry about things like planetary protection.
Yes. Planetary protection or planetary defense is sometimes what we call it, defending our planet from potential impacts. And Bennu is in a special class, and I think Dante spoke about this a little earlier, that Bennu is actually a near-Earth object, or a NEO. And a NEO, or near-Earth object, is an asteroid or a comet that orbits the sun, much like our planets do, but they're slightly unusual.
Osiris has reached the third and final natural feature tracking attitude. The spacecraft will hold this fixed attitude until tag.
Excellent. Great news. So back to NEOs.
Yes.
So NEOs are somewhat unusual in that their orbits bring them within the vicinity of Earth's orbit. The technical definition of a NEO is something that comes within about 30 million miles of Earth's orbit. And asteroids actually come close to the Earth all the time. 1 or 2 per week actually pass in between Earth and the Moon. But most of those are really small and not dangerous. But asteroids of a much bigger size that could actually do damage to the Earth's surface if they were to impact, they can pass by Earth closer than the Moon about once per month. And that's why it's really important for us to find them as early as possible so we can track their orbits, study their characteristics, and if necessary, we can mitigate a potential future impact threat. And that's where a mission that we're building now called the Double Asteroid Redirection Test, that's where DART comes in. And DART is going to launch in next summer, 2021, and it's going to test something we call the kinetic impactor technique. That could be used one day to help us mitigate a future potential impact threat by bumping an asteroid ever so slightly that's on a collision course with our planet into a slightly different orbit so it misses Earth.
Just a little bit is all you need.
Just a tiny bit.
So, I mean, that is really exciting. Now, I also understand that not all of the asteroids in the solar system are the same. There are different sorts, and NASA has some upcoming missions to study these different kinds of asteroids. So tell us a bit more about that, please.
Absolutely. Yeah, we know that the majority of our asteroids are found in the main asteroid belt between Mars and Jupiter. And in fact, we have a mission that's going to launch in 2022. It's called Psyche. It's going to visit one of the biggest asteroids in the asteroid belt that's actually called 16 Psyche. And this mission is going to arrive in early 2026 and help us better understand if this asteroid is potentially actually the core of a planet-sized object. We also have other types of asteroids called Trojans that are clustered in two groups that lead and trail in Jupiter's orbit due to a balancing act of the pull of both Jupiter's and the Sun's gravity on them. NASA has a mission to those Trojan asteroids called Lucy. It's going to launch next fall, about a year from now, and it's going to go visit several of these Trojan asteroids. We have a new mission called Janus, and we selected this mission through our Simplex small mission program line. This mission is going to send actually two small spacecraft, very small spacecraft, to two binary asteroid systems and help us understand what it is that makes these binary asteroid systems different from one another. And so studying this full breadth of these diverse small worlds will continue to help us fill up the knowledge gaps of how our solar system actually formed and evolved over time.
So it seems with all these missions coming up, we're sort of in a golden age of asteroid exploration. But then there's this other aspect of the Osiris-Rex mission, which is the sample return. And it turns out that we're also beginning this golden age of sample return to it, and not just to asteroids.
You're absolutely right. And we're really excited about all of these samples because they're so precious and there's so much science we can do with them. In addition to Osiris-Rex, we're also partnering with the Japanese Space Agency on their mission called Hayabusa 2, which is actually already on its way back, bringing a sample from Ryugu. They're going to be coming back to Earth in December. We're also partnering with Japanese Space Agency on another mission of theirs that's going to return a sample from Phobos, which is one of the two moons of Mars. And then finally, at the end of this decade, we're going to send a mission to Mars to retrieve the samples that are collected by the Perseverance rover, which is really truly our first astrobiology mission from NASA. And it's focused on looking for finding potential life, ancient life, on Mars. So sample of return is really important because it allows us to study these pristine samples back here on Earth. We can then take advantage of our room-sized laboratories. All of this.
OREX off. OREX has begun moving the solar arrays to the Y-wing configuration to avoid possible contact with the surface during tag.
Great news, moving right along. So when we bring the samples back, this allows us to use all of the laboratory capabilities that we have here on Earth. We can use the full suite of the scientific instruments that we have at our disposal to help us better understand the sample, their compositions, and the history of the body from which they came. And also having the samples back here on Earth allows us to preserve them for future generations to come and allows the future explorers to analyze the samples using techniques and instruments that haven't been invented and to ask questions that we don't even know to ask yet.
That is just so cool. I mean, life is all about how we navigate unknowns. This is something that's happening in real time around us tonight. So it's reassuring to know that there's an organized plan that you're in charge of to help take some of the uncertainties out of at least one dramatic category. So Lori Glees, thank you for joining us this evening. So good to see you.
Thank you so much for having me. I just want to add that it's been fantastic to watch the Osiris-Rex mission so far, and I'm really, really excited for what's ahead tonight, and I want to say congratulations to the entire team.
Thank you so much.
Thank you.
Now, asteroids are not easily navigated. They're hard to see, they have low gravity fields, they're dark and rocky, and traveling around the solar system where everything is moving rarely means traveling in a straight line. Let's take a look at some of the big challenges the team has faced to get to this point.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the Osiris-Rex spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down-select to 4 sites, and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position velocity in relation to the sample site.
And then the match point burn, about 10 minutes later, will zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag, we actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop a hazard map, which we program into the computer and says, if you're getting too close to those hazards, we'll do a wave off, we'll back away from the asteroid, and we'll come back and do this another day.
Everything might work perfectly. We come down, we touch the surface just where we want to, we fire the gas bottle, but the area we contact is covered in large rocks. Those rocks would prevent any fine-grained material from being stirred up and captured in the tag SAM head. Another similar scenario is if the tag SAM were to touch on the edge of a boulder and become tipped up. In that case, when the gas bottle fires, much of that gas escapes out the side, not churning up the material that we want to capture. The day of tag is going to be really exciting, but the excitement for our team doesn't end there.
We have to verify that we have a proper sample.
First, we're going to image the tag SAM head by sticking it in front of one of the cameras. Then we're going to do a maneuver called the sample mass measurement, in which we stick out the arm and we spin the spacecraft in order for us to decide if we've collected enough mass to be able to stow the sample and return home, or if we have to try again.
This is the culmination of a lot of work. It's probably one of the most exciting missions that I've worked on.
It is really exciting to know that we're finally going to be able to touch the surface of the asteroid and collect the sample to return back to Earth.
So step back for a moment and realize that tonight's events are exceedingly rare and historic. Humanity has only landed on a few different bodies in the solar system, and actually retrieving a sample is even more rare. So luckily with me tonight are some of the people that know better than anybody all the challenges that it took to get here. So let me introduce Mike Moreau. Mike is the Osiris-Rex Deputy Project Manager at the Goddard Space Flight Center, and Coralie Adam is Tag Navigation Manager at Kinetics Aerospace. So welcome, Mike and Coralie. How you guys doing?
So excited.
So excited. We're less than a half hour from tag now.
Yeah, you can feel the energy all building. So I should mention at this point that it's possible, you've been hearing this before, cheers from the MSA. So can you give us a sense of what's going on right now?
Yeah, so every few minutes a navigation camera image is taken by the spacecraft of the surface below, and it's sent to the natural feature tracking system. And that system identifies features in the image and sends a signal back to Earth that it was successful.
Position uncertainty is 0.5 meters.
And the team celebrates. It tells us we're on track to our next target and on track to tag.
Absolutely. So now, clearly there's a lot to talk about in terms of the mission, but once again, you had to do all of this in the midst of this COVID-19 pandemic. So were there any mission expectations that changed? How did you deal with that?
Yeah, for sure. I mean, as the whole world was coming to grips with the pandemic in the March timeframe, this team was in the midst of preparing for our first TAG rehearsal, the checkpoint rehearsal that would take the spacecraft only 65 meters above the surface. So we had to rethink the entire way in which we were going to do that rehearsal with only a skeleton crew here in the building and with many of our team members remote, as Sandy mentioned before. Today we have people literally all over the building monitoring, also at Goddard Space Flight Center and at the University of Arizona watching this event today. But thankfully we got through checkpoint rehearsal in April and match point rehearsal in August.
And all those special considerations, they're still going on around us today, right?
Yeah, I mean, you could see people spaced out in the MSA when you were over there. And, we had more time to prepare for TAG in order to accommodate that and get everyone into the building here today. So I'm just incredibly proud of our team for, their efforts to keep the project on track for TAG in spite of all of these challenges.
Absolutely. So I know NASA's famous for having to deal with unexpected situations, and this COVID-19 thing is kind of a different flavor of unexpected situations.
Whole new level.
We're going to deal about that. Okay, so now let's talk more about the challenges of TAG that we introduced in the video segment. So Corley.
Right, so you've seen that Nightingale site is an extremely challenging spot to navigate into. There's boulders all around it. This is totally different than how we originally designed the system to target a 50-meter diameter area. Nightingale is 10 times smaller than that. So it required the whole team to rethink how to safely navigate into the contact with the surface, and we had to come up with some new ideas.
Yeah, so the original navigation approach used LiDAR, or laser-based navigation, to take us to the Nightingale crater. But when we saw what Bennu looked like, we realized we had to switch to a vision-based approach, and that's the NFT system that you've been hearing about.
Yeah, so the Kinetics navigation team has spent the last 2 years learning how to navigate around Bennu using optical navigation techniques very similar to what NFT is doing on board the spacecraft today. So Kinetics worked with scientists and the Lockheed Martin NFT
OREX
team
MFA on
to
OREX Ops.
map the surface of Bennu.
OREX has processed its next image. Position uncertainty is 0.5 meters.
Really honing in. So we mapped the surface of Bennu to unprecedented resolution of 2 centimeters per pixel, which is better than what we've done on our own Earth and Moon. So it was a huge Herculean effort to get to this point where we're comfortable handing the maps and the keys over to the spacecraft to get us down into this small site today.
Absolutely. So I guess right now it's time to say goodbye to you guys. The best of luck for today. I'm really excited, and it's great to be with you guys.
Thank you, Michelle.
Yeah.
Thank
well,
you.
so right now, I think probably the best thing to do is to check in with Gary Napier. I guess we're going to go back and see how things are going back there. So to Gary.
So things are going really good right now, Michelle. We're actually going to talk to Heather Enos here,
OREX
the
MFA
Deputy
on OREX
Principal
Ops.
Investigator
OREX
for the
solar arrays
Osiris-Rex
are in
mission
the
out of the
Y-wing
University
configuration.
of Arizona. Thanks for joining us, Heather.
Hi, Gary.
So what's really interesting, Heather, is that you actually feel that, long missions like this are really important. I mean, you go from design to build, but operations is really quite a while. That it's actually really important to involve that next generation and kind of bring that generation up, correct? Talk to us a little bit about that.
Absolutely, Gary, you're right. All the way back from when we started planning this mission, Osiris-Rex, we recognized it's a long duration mission. And although that presents challenges for retaining your key personnel, we actually took it as an opportunity to use this mission to train our next generation of students and science engineers and scientists. A good example is we had one of our science instruments is called Rexus. It's an X-ray spectrometer built by a team of students at MIT and Harvard. So real hands-on.
That's really interesting. I mean, I understand you also have some folks that actually were students and came onto the team later?
Yeah, so being at the University of Arizona on a PI-led mission, we have had hundreds of undergraduate and graduate students working on this mission over the course of the last decade. And 2 of our students that started off as students are actually 2 of our navigation team members. That's Dan Wibben and Eric Sarr.
Wow,
so
they're on console.
they're on console right now. Yeah, they are.
At this time, NFC has
so
computed the checkpoint and match point burn updates to correct for errors in the trajectory accumulated since orbit departure. Checkpoint burn in 2 minutes.
So checkpoint turn in 2 minutes. We're going to throw it back over to Michelle, because I know this is an important update for her. So Michelle, thanks. Back over to you.
Thanks, Gary.
Well, absolutely. So, Dante, tell us what this important milestone checkpoint means.
This is a really important part of the mission right now. So we've been hearing about natural feature tracking and how it's processing these images.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 0.46 meters.
Right, so what it's doing with that information is it's calculating how it's going to fire its thrusters for this checkpoint. When we left orbit, we were on a trajectory that would take us over the surface of the asteroid, and if nothing else happened, we would safely fly past Bennu. Once we fire the thrusters for the checkpoint maneuver, we're actually going to start descending down towards the asteroid surface, so this means we're going to be on our way to make contact. So natural feature tracking has been doing nothing but calculating this maneuver since we started taking images.
So this is one of the big deals. This is one of the big milestones coming up.
This is huge.
Yeah.
Absolutely.
I know that as we look at the simulation, there's an interesting configuration the spacecraft is in. Oh, I see the thrusters firing.
That's right. You can see we would expect right now on the spacecraft the thrusters to be firing, so we're going to be paying close attention to Dale Howell to let us know we've gotten telemetry back to telling us that maneuver has succeeded.
In the meantime, if you want to tell us a bit about the configuration it's in, go ahead.
Yeah, we heard Dale call out earlier that the spacecraft was in the Y-wing configuration. There we just reconfigured the solar arrays to get them up away from the asteroid surface, basically to protect their active areas from any dust loading that might be kicked up during the tag event.
It's another excellent Star Wars reference.
That's right, always. You can also see here in the simulation the Nightingale sample site, now down in the lower corner here. This is our target. This is what we're trying to get into with that spacecraft. So.
Now, it looks like there's a lot of boulders around that.
Yeah, as we've said, generally the surface of Bennu is rough and rugged and covered with boulders. Nightingale really does stand out as a pretty unique, interesting area on the surface.
How you doing?
Doing pretty good. Paying close attention to that call out, waiting for Dale to tell us that checkpoint has occurred.
Absolutely. So what we're waiting for right now is the call out that checkpoint has occurred, and the Osiris-Rex spacecraft has begun its descent towards the asteroid surface.
Right. Any time now.
And it's probably worth mentioning.
OREX MSA on OREX Ops. Checkpoint burn has completed.
Okay, we're heading down towards the asteroid surface at this point.
Oh, wow. Oh, wow. Okay, well, you know, I guess the next thing that comes up is going to be this match point maneuver. So that's the next big milestone for us.
That's right. So we've got one more firing of thrusters with the spacecraft to get us lined up for the sample acquisition event. We call that the match point because what we're doing there currently as we're flying over the asteroid surface, in fact, it's the asteroid surface that's rotating underneath us. Mm-hmm. And when we fire thrusters for match point, we're doing that to match that rotational velocity so that the spacecraft becomes station keeping essentially over that Nightingale sample site.
Mm-hmm, absolutely. All right, so I think we have a little bit of time now to turn to our social media desk. So James, what's going on in social media?
Yeah, Michelle, it's super exciting. You just heard that checkpoint burn confirmed. We are now just very, very close down to the surface of Nightingale. And you guys have been really excited over on social media too at that hashtag to Bennu and back. Lots of great messages rolling in here. Someone's really excited for our little robot friend to go rock hunting on the surface. We had someone who actually attended our launch back in a couple of years ago at Cape Canaveral and are now watching the broadcast live with us today, excited for that sample collection event. We have Philip who kind of puts it in perspective for us here. He says, this is amazing and extremely difficult in so many ways. Bennu's orbit, spin, inclination, the orbital mechanics of this long mission are just astounding. I can only imagine how many orbit simulations have been made here on Earth. It really is a crazy mission, and we also have our animal friends, our pets, cheering us on here as well. Bennu is rough from this couple of our pets here, really excited. So we're now just minutes away from that match point burn, and for that, I'll kick it back to you, Michelle.
Okay, excellent. So, you know, just a few minutes ago, Dante, you were saying that this landing site is sort of a unique area on the asteroid. Tell us about this site.
Yeah, we spent an enormous amount of effort selecting the area on this asteroid surface where we wanted to get the sample from. And we kind of divided our analysis up into 4 different categories. First, we were looking at the deliverability. And this was a real challenge because, as we've seen earlier in the broadcast, the original guidance accuracy was 25-meter radius, and we're trying to get into an area that's 10% of that size. We have solved that problem with our amazing natural feature tracking solution, and as we've heard, That's worked really well, and it has updated its checkpoint and its match point maneuvers on board based on that information. That gets you down to the surface of the asteroid. So the next thing that we have to worry about is maintaining spacecraft safety. There's a lot of hazards on this asteroid surface, things that could damage a critical component, and we decided to focus safety on the things that were needed to get the sample back to the Earth. So there were certain things we could lose at this point in the mission if they didn't fulfill that objective. We still have some upcoming major milestones that help us maintain that spacecraft safety. Now natural feature tracking is going to be switching over to calculating the contact point on the asteroid surface. And it has a piece of software on board called the hazard map. It's actually determining, is the location that I'm going to touch down on safe, a green area on that hazard map, or is it potentially hazardous, a red area on that hazard map? So as we get closer to the asteroid surface, a key moment is the 5-meter crossing. That's when the spacecraft makes that decision. Do I continue down to collect the sample, or do I back away and live to tag another day? After that, you've got down there, your spacecraft is safe. There's got to be something for you to pick up. Earlier in the broadcast, Bo Bierhaus showed us the size of particles that TAGSAM could actually collect. So we had to map the Nightingale area and other potential sample sites well below that 2-centimeter resolution. And in fact, we got 3.5 millimeters per pixel all over the Nightingale sample site. And we were really excited to see lots of particles of that size. And of course, the final parameter that we were looking at was the scientific value. And I can tell you the good news is any sample from Bennu is scientifically valuable. We've seen these hydrated clay minerals, we've seen organic molecules, carbon-bearing minerals all over the surface of the asteroid, exactly the kind of material that we're hoping to bring home.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. And that's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface. And the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to collect that sample.
Of course, the amazing thing about match point is that the asteroid itself is actually rotating. So when we go to match point, the spacecraft has to match the rotation of the asteroid so it comes directly down onto it.
That's right.
So how fast is Bennu rotating?
Bennu has a rotation period of 4.3 hours. So that's basically the length of the day on the asteroid. On Earth, the rotation period is 24 hours, which is why a day on Earth is 24 hours long. So that translates, because Bennu's a pretty small object, as we've seen, 500 meters or about the same size as the Empire State Building. At the equator, the surface is moving at 10 centimeters per second. And it actually gets slower and slower as you go to higher latitudes. By the time you get to the North Pole, it's 0. Nightingale's pretty far north, so it's actually much lower than 10 centimeters per second. And that just kind of shows you the delicate precision nature of this mission. You know, we've got to get very low thrust maneuvers, very delicate, very slow approach to the asteroid surface. Everything kind of happens in slow motion when you're operating in a microgravity environment like Bennu.
So what's the next critical milestone after match point?
After match point, we're going to be looking for the natural feature tracking system coming back online, taking those images and additional correlations and precision on its knowledge of its position. And we might expect it to actually jump up. We've been hearing natural feature tracking uncertainties on the order of half a meter. It may go up a little bit as it goes through.
on OREX Ops. OREX Natural Feature Tracking System has resumed processing. Position uncertainty is 1.6 meters.
So you can see there we went back to 1.6 meters. That's because we went through the checkpoint maneuver. So whenever you impart a thrust like that, it adds uncertainty into the system. And we're seeing that with the natural feature tracking system right now.
That is so exciting. Okay, so we're going to introduce, actually, the Associate Administrator of NASA, Dr. Thomas Zurbuchen. Thomas, thank you for joining us.
So glad to be here with all of you.
It's an exciting time, Thomas.
Happy birthday.
Thank you.
Yesterday,
That's right. Yesterday's his birthday. Yeah, that's right. Happy birthday. So, I guess, everybody here is aiming for this point in time called this TAGSAM, but it turns out that there have been a lot of friends, a lot of colleagues that have helped get us to this moment. So, who's been along with us on this journey?
Well, look, I mean, there's a number of course, domestic partners, many of them around here. You talk to some of them, but there's also international partners, and the Canadian Space Agency provided the laser altimeter, which is an important instrument here. And of course, we have a partnership with JAXA. What we're going to do is actually share the samples from Ryugu, from Hayabusa 2, with Osiris-Rex once it's back for maximum science, and that's really what international partnerships are about.
So this is a big mission for NASA, but it turns out that there are many different kinds of partners in a mission like this. Give us a sense of the range of partners that we have.
Well, look, I mean, it starts with the University of Arizona. That's where the leadership is, and with you there and your entire team. But NASA Goddard Space Flight Center is a critical partner with managing, of course, especially also working with Lockheed Martin, who really, with that team deserves a lot of credit, and Kinetics, which was already introduced, as well as many others. If you really look, so often missions like that touch many, many states around the United States.
Absolutely. So, Thomas Zurbuchen, thank you for joining us, and we will see you later on in the program.
How do you feel, man?
I'm pretty excited. This is the final 10, 12 minutes here for contact. I feel really good. The team's in high spirits. As you and I talked about earlier this week, we have done everything possible to make this today a success.
Exactly right. And your mind is already out there, and the spacecraft is already on the way out in real time. Can you imagine that, right?
It's good actually to point out whatever has happened with TAG has already happened. We're well past that 18.5-minute one-way light time.
Absolutely. Hey, congrats. Let's continue doing this.
Yeah, we'll see you later. Thank you, Thomas.
Yep.
Oh, wow. Okay, so we're coming up, I know, on the critical point of match point. So
That's right.
At what point will we know that we really have a sample?
That's a great question. We're not exactly sure what's going to happen right away. We'll know if we made contact with the asteroid surface today. We'll know if the gas bottle fired, and we know that we backed safely away from the asteroid. But we actually have a lot of work to do over the next week or so. We'll take a look at the images that we were acquired during contact with the asteroid surface, and then we'll go into a different imaging campaign. We're about 30 seconds from match point, so we're going to keep our ears open for that critical call out from Dale.
OREX MSA on OREX Ops. OREX has processed its next image. Position uncertainty is 1 meter.
All right, we're back down to a meter positional uncertainty. That's great news. So back to sample verification. We will, after we're well away from the asteroid and everything has kind of settled down, we have that robotic arm. We're actually going to use that to put the TAG SAM head into the field of view of SAMCAM. And we can look not only at the top of the sampler head like we're going to get with the images today, but we can actually turn it around and we can look at the base of TAG SAM. We have, in addition to the gas stimulation, we have contact pads. Simply by making contact with the asteroid surface, we think we can pick up fine-grained particles less than a millimeter or so. But basically, we're going to be looking for any evidence of asteroid material on or inside the TAG SAM.
Now, obviously, you don't want to go all the way back to
OREX
Earth without...
MSA on OREX Ops. Match point burn is complete.
All right. We're heading down. We've got about 10 minutes before contact with the asteroid surface.
Oh, wow. So I was about to say, so obviously you don't want to head back to Earth with not much sample. So how do you know how much sample you actually got?
There's an incredibly clever physics experiment that the team has designed here called the sample mass measurement. So what we're going to do is we're going to place the spacecraft arm out to the side of the spacecraft. So when it's in sampling configuration, it's actually pointed above. For this, we point it out in the other direction and we kind of spin the entire spacecraft around. And we're measuring a property called the moment of inertia. We have actually already done this prior to initiating the TAG sequence today. So we know what that property is when the TAG SAM head is empty. Now we're going to be able to do it, hopefully, when it's full of asteroid regolith. So we're only looking for small differences in this property as a result of this experiment. And the precision, just like everything on this program, is phenomenal. We're talking tens of grams of precision on a measurement on a spacecraft hundreds of millions of miles away that just picked up this asteroid sample. The minimum that we're looking for is 60 grams, or about 2 ounces.
MSA on OREX Ops. Attitude control system has transitioned to touch and go mode.
Right, spacecraft's getting ready to make contact with the asteroid surface here. So the sample mass measurement will tell us if we have 60 grams or more of material, and that'll happen on Saturday later this week.
Excellent. Okay, Dante, this is it. You know, the engines have given us a push in the right direction, and Osiris-Rex is on course to make touchdown on an asteroid. So we're going to listen to the flight controller calls from MSA, but before we actually touch the surface, it's a great time to visit our social media desk again. So, James, what's going on?
Yeah, thanks, Michelle. So you've been hearing those call-outs from Dale over the loudspeakers about those NFT images processing. It'd be awesome to actually grab a camera and make the trek out to Bennu to photograph it up close in person. But, you know, as we've mentioned, Bennu is a little bit far away from us right now, on the order of 200 million miles away. But don't worry, here's something Osiris-Rex can deliver to you right now from the comfort of your own home. If you're on Instagram, you can head over to @NASA Solar System. We have 2 AR filters that you can use on your social media stories. This first one's called Osiris-Rex and You and features Osiris-Rex playing tag with Bennu around your head. The second one is called To Bennu and Back and allows you to place an asteroid wherever you are, at home, at school. Bring an asteroid with you. So I understand we actually have a question coming in from Instagram from Mauricio, who asks, how do you manage the force back from touching down? I mean, the moment the spacecraft touches the surface, it should experience a similar force in the opposite direction. How do you manage that? Well, thanks Mauricio. So the team actually thought ahead for this one when designing that sample arm. They actually added the spring-like mechanism to it that you can think of a bit like a pogo stick. If that sample arm were rigid, when contacting Bennu, it would stop its downward motion, and when firing the gas bottle to stir up a sample, we would just kick right back off into space, as Bo Beer has.
We're going to start looking at those later tonight and have them available for everybody tomorrow morning. So this is just a simulation of the field of view of the SAMCAM, the sampling camera, part of our OCAM's camera suite. It has a clear shot of the TAG-SAM collector right in the middle of its field of view. You can actually see the lower end of the TAG-SAM arm here.
OREX MSA on OREX off. OREX is descending below 25 meters.
Okay, we're getting really close. And I want to remind you, it's the 5-meter crossing.
Yeah.
That's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live the tag another day. So to me, all my senses are on that call out right now.
Yeah.
I really want to hear that we are go for tag, so that's just a couple minutes away here.
And of course, remember that that was planned for. That
That's right.
It has to know it's safe, otherwise it's going to back up and try again another time.
That's really how we solve the amazing challenges that this asteroid surface presented to us. You can see here that this is a pretty daunting terrain that we're coming down here. There's giant boulders all around the Nightingale site, even some large rocks inside the crater that we do not think the spacecraft would survive, at least with the ability to return back to Earth if it made contact. So it is there to protect itself first and foremost. Safety is always first, but we're feeling pretty good. Everything's gone really well today, so I would say things are looking great for a tag, but of course the spacecraft is the one that gets to make that decision.
It's just amazing. You know, we've been rehearsing this event, you know, all week long, all the different mission calls and milestones, but then to actually be here tonight and realize that this is going on 200 million miles away.
That's right, yeah. I'm pretty excited.
So, I mean, there were obviously a lot of firsts in this mission.
OREX MSA on OREX ops. OREX has processed its next message. Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounds like the hazard map calculation looks really good. We're coming down in a green area. We're going to make contact with the asteroid surface.
Wow. So remember how historic this is NASA's first mission to retrieve a sample from an asteroid,
Yeah.
a pristine part of the solar system.
That's
Just
right.
look at that animation now. So we're looking
I'm looking at the team. I think that, I think we can see everybody is laser focused on what this spacecraft's going to do. So I say let's let this play out. But those calls were really great. That was great news from Dale.
Yeah. Even more accurate than we'd hoped for in some cases.
Everybody seems happy.
Yeah. So I guess, there were obviously a lot of firsts in this mission, and there was a time when you said, a lot of what ifs basically. I mean, what if we could actually send a spacecraft to an asteroid? What if we really could bring back a sample of the solar system from billions of years ago? Do you remember where you were when those what if
OREX
questions?
MSA on OREX off. OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
Touchdown declared.
All right.
Sampling is in progress.
Oh my gosh, we're there, folks. That was amazing. I mean, I don't know if you saw the team here, but they just kind of blew up. They went from being steely-eyed to like celebrating the Super Bowl. So, it's all good. This is amazing. So congratulations, everybody. I know that Dante and Dr. Zabrukin are right here. And Dante, you somehow got over here pretty quick.
I sure did.
Congratulations. How you guys feeling?
Transcendental. I mean, I can't believe we actually pulled this off.
But I'm so excited about the team.
Yeah.
Hey, do you mind if I just bring up something?
Please.
Our friend Mike Drake is with us right now.
That's
the
right.
guy who came up with the mission at the beginning, and we're thinking of him. He's no longer on Earth, but I feel him right here.
I agree. He's with us today, and I know he's incredibly proud of this team and everything we have accomplished. This is history. It's amazing.
God, I can barely speak. You know, I'm like shaking. How about you?
Absolutely. It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
All stations, this is systems. I can confirm that the backaway burn is...
OREX MSA on OREX Op. Sample collection is complete, and the backaway burn has executed.
All right.
We're on our way back.
Now, Dante, that was actually a really important call. We were celebrating on the tag,
Yeah.
but that was actually probably even more important call. Why is that?
The pyro bottle's fired, so tag SAM operated. The backaway thruster's fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. So we did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went.
What does this mean to NASA?
Oh, I mean, this is key milestone of this. Now it's a few days, right? To figure out how much we caught of this amazing sample that
That's
we're
right.
thinking about for decades. But I think this is just, I'm so proud of this team. Hey, team.
Oh my goodness.
Oh my goodness.
Well, I got to tell you, this has been a fantastic day, a fantastic journey. We're so proud of both of you for being here and supporting that team. We're going to get back over to the stage and Michelle, but some really good news. So back to you, Michelle. Thank you.
This is one of those moments we're all aware of COVID-19 because I want the hugs and the high fives and everything, but we're all going to keep each other safe. There are lots of super excited people all over who want to share in this moment and share their congratulations.
No kidding.
So let's take a moment
goodness.
to hear a few words from three institutional leaders who couldn't be here tonight, but they're cheering on the team on behalf of so many supporters.
Hi everyone, Dennis Andrusick, Goddard Center Director. I am just so excited that Osiris-Rex is collecting a sample from the surface of Bennu. The tag is just the pinnacle of the mission so far.
MSA on
Getting the
OREX
sample
Op.
back to Earth is
OREX
obviously going to be
has
the
completed
great event
the
of the
backaway
entire
burn
mission.
and is
But I got to
pleased to
congratulate
Pegasus
Dante, you and your
attitude to
team,
recharge.
your project management skills as a PI, just superb. Rich, the operations team for getting us to where we are, and Lisa Callahan for the awesome Lockheed Martin team in getting Osiris-Rex to where we are and building a great spacecraft and returning it to Earth. Go Osiris-Rex.
Today's an exciting day. As Osiris-Rex begins its descent to Bennu, the nation is looking forward to the news of a successful tag event. Osiris-Rex team members have been working on this project for more than a decade, and the work being done is hard, and it's complicated, and it's necessary. Understanding the makeup of Bennu will help us better understand our universe and how to protect our most important asset in space, Earth. I want to wish the best of luck to the entire Osiris-Rex team, including our partners at the NASA Goddard Space Flight Center, the University of Arizona, and especially the mission operators and engineers right here at Lockheed Martin. Go OREX!
The University of Arizona is incredibly proud of its long tradition of excellence and leadership in space exploration. I'm thrilled to see the Osiris-Rex's mission's achievements carried this tradition forward today with NASA, Lockheed Martin, and all of our incredible partners.
Congratulations to all of the Osiris-Rex mission team members. You have shown the world how our determination, creativity, and talent can advance the capabilities of our entire nation. And I can't wait for the amazing science we will see with the sample return in 2023.
Okay, well, we are here live after some excellent news. I'm here with an exultant Tante Loretta from the University of Arizona. So one more time for our audience out there, explain when we know we'll have a sample.
A little overwhelmed right now, Michelle, I have to say. It's been pretty intense several minutes here. I can tell you that everything went just exactly perfect, which is kind of the hallmark of this team. We have consistently beaten expectations over and over again. We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We made it down to the asteroid surface. We were in contact. The gas bottles fired. We don't know how long we were in contact with yet. That's some reconstructed information that we're going to have to put together over the next few hours as the data come in. We backed away successfully from the asteroid surface. The team is exuberant back there. Emotions are high. Everybody is really proud, and we have some work to do to determine how much sample that we have collected. The next thing that I'm going to be looking for is once the spacecraft cools off, it probably got pretty warm as it approached the asteroid surface, so it needs to get rid of some of that excess heat. It's got to get those solar rays back onto the sun and get power positive. Once it's stabilized, it's going to point that high gain antenna at the Earth, and we're going to start bringing that data back. And those SAMCAM images are going to tell us an enormous amount of information about how the events of today went. We're going to be looking at a whole series of images as we descended down to the surface, made contact, fired that gas bottle, and I really want to know how that surface responded. We haven't done this before, so this is a new territory for us. And the whole science team, I know, is really looking forward to that information. For one thing, it'll tell us the likelihood of sample collection, kind of a probabilistic assessment. Probably be a lot of science that comes out of that as well.
Yeah, well, listen, I know you want to be back there with your team. It's going to be a long, hopefully happy night for all of you as more data comes in. Thank you so much. It's been such an honor to be with you.
Thank you. Thank you, everybody, for a great evening. And kudos to this team. It's an amazing experience.
Oh, wow.
And history was made tonight.
Absolutely. Sure. So, you know, what we're going to do now is actually take a closer look at this beautiful terrain that we've actually sampled. We've identified over 1 million asteroids in the solar system. But remember, Bennu is what's called a NEO, a near-Earth asteroid. So instead of orbiting in the main asteroid belt between Mars and Jupiter, it has an orbit fairly similar to our own planet, Earth. And it not only gets our attention because it's so close to Earth, but also because we believe it may be one of the older bodies in the solar system with a wealth of information about how the solar system and life began. Let's take a closer look at the subject of all of this activity, all of this joy tonight.
Thank you.
Let's take a tour of Bennu.
In December 2018, after traveling for 2 years, 101 days, and over 1.2 billion miles, NASA's Osiris-Rex spacecraft arrived at its target, near-Earth asteroid Bennu. Osiris-Rex is the first mission to explore this primitive remnant from the origins of the solar system, designed to study the asteroid and return a sample to Earth. Bennu is a dark, diminutive world, roughly the height of a skyscraper, and now the smallest body to be orbited by a spacecraft. Prior to arrival, it was known to have low thermal inertia, a characteristic of fine-grained materials like sand. An infrared spectrometer on Osiris-Rex confirmed this property, leading scientists to expect a predominantly smooth surface. But the first close-up views of Bennu delivered a major surprise. In exquisite detail, the mission's cameras revealed an unrelenting rockscape dominated by boulders. By combining these images from Osiris-Rex with its laser altimetry data, we can take a tour of Bennu's remarkable terrain. The first stop is Simurgh Saxum. This prominent boulder defines the asteroid's prime meridian and serves as the basis of its coordinate system. In Persian mythology, the Simurgh is a large and benevolent bird and the possessor of all knowledge. Saxum is Latin for stone. To the northeast lies the largest boulder on Bennu. Measuring over 300 feet in length, Rock Saxum is a colossus longer than a football field. It is also rich in a type of iron oxide called magnetite, which was used by mariners as an early form of magnetic compass. In Arab folklore, the rock is an enormous bird of prey that can clasp elephants in its talons, as well as stranded sailors like the hero Sinbad. Continuing northeast over the equatorial ridge, we arrive at Gargoyle Saxum. This striking boulder is among the darkest on Bennu, though it clutches a much brighter rock that is about the size of a person. In medieval legend, gargoyles are dragon-like, winged monsters that can breathe fire and that guard cathedrals from evil spirits. Our next destination takes us far to the east. At the northern end of a small crater lies Osiris-Rex, a comparatively bright boulder measuring about 33 feet in diameter. Osiris-Rex is located near one of 3 sites where Bennu ejected small particles into space in early 2019, displaying its dynamic and evolving nature. In Greek mythology, Osiris is one of the 3 harpies, the half-maiden, half-bird personifications of storm winds, who would carry evildoers away from the earth. In the creation stories of ancient Egypt, the universe began as a formless, endless expanse of water. From this primordial sea arose the primordial mound, Benben. It was upon this rock that the god Atum settled in the form of the Bennu bird and sent forth the call that shaped creation. The story of Benben harkens to the mounds of fertile silt that once emerged from the receding floodwaters of the Nile, and it provides a fitting namesake for the tallest boulder on Bennu. Protruding by over 70 feet, Benben Saxum is so tall that it was first detected from Earth. Now, we can appreciate this monumental feature in detail using data from Osiris-Rex. The final stop on our tour is a cluster of exceptionally bright boulders scattered across the southern hemisphere. They bear the spectral fingerprint of pyroxene, a mineral found in igneous rock that is unlikely to have formed on Bennu. These boulders most likely originated on the large asteroid Vesta and were delivered to Bennu's parent body through meteoroid impacts. Although it is small in size, Asteroid Bennu has proved to be a fascinating world, abundant in geographic features that have defied our expectations. Thanks to Osiris-Rex, we can now explore Bennu to uncover its composition, its evolution, and its ancient memories from the origins of the solar system.
And if everything has gone right tonight, a little bit of Bennu will be coming back to Earth in 2023. So let's get one last visit with our social media desk. James, what's going on?
Yeah, Michelle, I've got goosebumps. I really can't even begin to fathom that we just tagged and collected a sample from this asteroid 200 million miles away. I know I'm going to want to relive the events that just unfolded tonight. I'm sure you will as well. So once again, we have that 360 video up on our NASA Goddard YouTube page. Go check it out and put yourself right where the action just happened a couple minutes ago. It's truly mind-blowing stuff. I also want to check back in with that Twitter poll that we put out at the beginning of the broadcast. And we were asking you how much material you think we just got from Asteroid Bennu. So remember, we're looking for at least 60 grams, but that sample container can hold up to 2 kilograms. So you guys are saying that a candy bar size of sample? I like the optimism. Let's hope we actually pack that container to the max and bring all the sample back home. But any sample we get back is truly magical and will help us learn more about the solar system and our origins here. So keep at us on the hashtag to Bennu and back. We're excited to keep this conversation going as we look to bring that sample all the way back from Bennu here to Earth in 2023. So back to you, Michelle.
This is one of these evenings where it's such a privilege and a pleasure to be working for NASA and for the idea of scientific exploration. So what we've been doing all evening is seeing the joy, seeing these people that have worked on this for decades. But you have to remember there's a real reason we're going to look at these asteroids. We think we actually might be coming back with a baby picture of what the solar system was like, of what our chemistry was like billions of years ago. We're looking for our own origins out there, and that's why we've gone so far to bring a bit of Bennu back. This has been an incredible evening. The adrenaline is slowly beginning to slowly go down, and there's going to be a lot of celebration and a lot of work in the coming hours. So from Lockheed Martin Space here in Littleton, Colorado, I'm Dr. Michelle Thaler. Good night.
We are ready. Go.
Hello,
okay,
everyone.
So I won't be providing descriptors, so what I'll do is just give a quick countdown for you all. Then I'll be stopping the music, okay? So in 3, 2, 1.
All right. Hello, everyone. I'm Nancy Neal Jones from the Office of Communications at NASA Goddard Space Flight Center. I'm standing in the mission support area at Lockheed Martin Space Facility. We are complying with local county guidelines and Lockheed Martin's social distancing policy of maintaining at least 6 feet when possible and by wearing masks. Yesterday, NASA's first asteroid sample return mission, Osiris-Rex, successfully made contact with the surface of asteroid Bennu to collect a pristine sample for delivery to Earth in 2023. To share some remarks with us and to tell us more about what happened yesterday and what's coming up for the mission, we have with us today Jim Bridenstine, NASA Administrator, NASA Headquarters, who'll be joining us by phone. Thomas Zabukin, Associate Administrator, Science Mission Directorate, NASA Headquarters. He will also be joining us by phone. Dante Loretta, Osiris-Rex Principal Investigator, University of Arizona. Rich Burns, Osiris-Rex Project Manager, NASA's Goddard Space Flight Center. And Sandy Friend, Osiris-Rex Mission Operations Manager, Lockheed Martin Space. We'll start with the Administrator, with Administrator Bridenstine joining us from his phone. Administrator Bridenstine, we turn it over to you.
Well, thank you. It's an amazing day. I just saw the first images there of Osiris-Rex touching down on Bennu, and it was every bit as beautiful as I thought it would be. What an amazing accomplishment by such amazing people at this time. We think about the challenges of getting Osiris-Rex built and launched. We think about, this has been a project that NASA and the University of Arizona and Lockheed Martin and all of our partners, we've been collaborating on since 2011. And I know University of Arizona was working on it even before that, trying to get it approved. And here we are in the year 2020 with this really stunning achievement. And I just want to say congratulations to all of the teams. The idea that this team broke the record for being able to orbit the smallest object that's ever been orbited before, the idea that they were able to orbit an object closer than any object has ever been orbited before, the idea that when we got there, we learned so much about how rough the terrain was, which was not anticipated, how small of a landing area we actually had, and then ultimately being able to use this extremely sophisticated precision navigation capability that way outperformed what anybody believed could be done. Of course, I know the people who built it believed in it 100%. But it was just, it was an amazing day yesterday when we watched it land on a parking spot. Basically, the area was about the size of 2 parking spaces side by side, and it landed just as it should have. We didn't get 5 or 10 seconds on the surface. We got 15 seconds. And of course, we're going to be learning more about how much sample we got and things like that. But it went as well as could have gone. I said it yesterday. I'll say it again. The Osiris-Rex mission outperformed in every way. And so I just wanted to make sure that I congratulated the teams. And you guys all made not just the United States of America proud, but you made humanity proud in your ability to go way out into deep space and characterize this asteroid Bennu. There's so much more to do. I want to be clear, there's a lot left to do. We've got to bring the sample home. But at the same time, this in itself, the touchdown, the sample collection, was an amazing achievement, and I want to congratulate the team. So with that, I'll turn it back over.
Thank you, sir. Thanks, Administrator. It's Thomas Zabukin here, and yes, yesterday our team did an amazing thing, a true first for NASA. The mission, of course, had its genesis in the early 2000s, like you said, and OREX finally had the penultimate act of its amazing journey when it successfully touched the surface of Bennu to collect a sample. we're going to hear about this, but everything really went like it should and like we hoped yesterday. The technology performed flawlessly, and the commands our great team sent to the spacecraft unfolded autonomously. Since the signal from the Earth to OREX is 18 plus minutes, and the spacecraft had to be preloaded and prepared for this amazing journey on its own. I remember thinking on multiple occasions down to yesterday, and Rich, wow, if only the speed of light was a lot faster. And it isn't, of course. The spacecraft slowly approached the surface of Bennu. Its data getting more detailed, and the risk going down, decreasing as we got more and more information and approaching that target with an accuracy unprecedented in previous tests. It then touched Bennu, and we're going to hear about this, blast into the regolith and stirred up a swirl of material, probably unlike anything Bennu had seen in quite a while. And then, as planned, evaluating its surrounding, the spacecraft backed away and is talking to its handlers on Earth. The team has a lot to work on to analyze, and it is likely to be a sample, and it appears that the spacecraft is safe. And again, I look forward to hearing the details here. This is all the beginning of the process, and we're nowhere near the end. This morning, in fact, I thought of the analogy of fishing. Yes, the line tightened and the sinker dropped, and we are excited, but now we need to bring it in, see whether we caught the fish, and then, of course, bring it home. It was an honor and a joy to be with the mission control team yesterday and the leadership team at Lockheed, and we determined that the spacecraft had done exactly what it was designed for, and apparently touched the surface and fired the gas bottle that powers the collection mechanism, the TAXAN, and is now safely on its way back from this hazardous environment. It's always an amazing feeling to be with people celebrating such a success for humanity, as the administrator said, one that took many thousands of people over many years to achieve. I know from my emails and text streams and social media that scientists within the United States and around the world are ecstatic. Discoveries we will make about our solar system and our planet from materials that was around at the time of its formation will be immense. And the questions that we have, whether or not these bodies could in fact seed life on Earth, is another tantalizing avenue we want to pursue, and many more. And it looks like many generations will have the chance to pursue these kind of questions and others from the pristine samples coming back to Earth. And countless discoveries and researches will be happening as a result of that. So Dante, Loretta, principal investigator, I want to commend you and the entire team at the University of Arizona, the team at NASA Goddard and Rich Burns and others, and Lockheed Martin, with the good people that we met there yesterday. I also want to give a shout out again to our international partners on OREX, the Canadian Space Agency and the Japanese Space Agency, who are our partners in asteroid exploration. And I really look forward with everyone else to hear from Dante and the team about the details of how we pulled off this incredible mission and what's next. Most importantly, I really look forward to him releasing what I believe will become an iconic image of the power and excitement of exploration, one that inspires all of us. Back to you.
Okay, thank you. Thank you, Administrator Bridenstine and Dr. Zabukin. We will now turn it over to Dante Loretta, the principal investigator of the Osiris-Rex mission. Dante?
Thank you, Nancy, and thank you, Administrator Bridenstine and Dr. Zabukin, for your words of support and encouragement. It was great to have Dr. Zabukin and Dr. Lori Glaze and other representatives from headquarters here yesterday supporting and encouraging this team, and we really appreciated Administrator Bridenstine's congratulations to the entire team yesterday. It uplifted the team to an even higher level after an amazing accomplishment, and we really appreciate you joining the team in our celebration. So yesterday was all about monitoring this real-time telemetry from the spacecraft as we watched the events unfold 200 million miles away. And the question that came up over and over again in that live broadcast was, when are we going to get the images back? When are we going to know how the sampling event went? I can tell you, a lot of us were up really late last night. We were watching the images come down one by one. By about 2 a.m. here, local time in Denver, we got what I call the money shot, where we saw tag sand contacting the surface and then the effect of injecting that high purity gas down into the asteroid regolith. So I think without further ado, let's just go and take a quick look at the data. I'm going to show you a series of images taken by the SamCam. This is about twice the frame rate, so we're coming in a little bit faster here. And I'm just going to let that play out. I'm going to let you appreciate it one more time as we go through. And then we've got some analysis that we can perform about what happened here. Maybe one more time. It's just so cool. I must have watched it about 100 times last night before I finally got a little bit of shut-eye. And then I dreamed of a wonder world of Bennu regolith particles floating all around me. So just to remind you what we're looking at here, this is a full-scale model of the TAG-SAM head. And so this is what's at the end of that long robotic arm. You can see it's about 30 centimeters or about a foot in diameter. And this is what we placed onto the surface of the asteroid. It's at the end of the robotic arm, and the high-purity nitrogen gas feeds in here through a couple tubes, and then it actually comes out through this inner annulus and pushes everything up into the collection chamber. Let's take another look at just a couple of the key images right before contact and right after contact before the gas is fired. So there's a little over 1 second time difference between these two images, and there's an enormous wealth of information about the asteroid surface contained in here. So the first thing that you can see, if you look at the area right above about the 12 o'clock position on the sample head, we're making contact with a relatively large rock, a little over 20 centimeters, which we had considered a potential obstruction to sampling, but literally we crushed it. When the spacecraft made contact, that rock appears to fragment and shatter, which is great news because that means that ingestible material by TAG-SAM is probably being created just by the motion of the spacecraft pushing into the surface. If you look at a couple other areas around, like this one here about 1030, just off to the upper left of the TAG-SAM head, you can actually see motion in the regolith. So it looks like we are pushing and exerting a force throughout this soil on the asteroid's surface. Also good news for our potential for successful sample collection. I want to point out another feature of the TAG-SAM head that didn't get a lot of attention yesterday. We talked a lot about the gas stimulation and driving bulk sample into this filter. But as you can see in this 3D printed model of TAG-SAM, there's a whole series of circular discs. On the flight hardware, what's mounted in here are contact pads, literally made out of stainless steel Velcro. And these are designed to pick up material on the order of a millimeter size and smaller. So the fact that when the TAG-SAM head is making contact with the asteroid surface and it's crushing what appears to be a very soft, friable material is good news not only for the bulk sample collection, because in our laboratory tests, when the TAG-SAM head penetrates, and we're estimating about 2 centimeters of penetration at least during this event, a lot of material gets forced up into the sample collector. And of course, by crushing, you're going to drive a lot of material into these contact pads. So right away, bottom line is, from analysis of the images that we've gotten down so far, is that the sampling event went really well, as good as we could have imagined it would. And I think the chances that there's material inside the TAG-SAM head have gone way up based on the analysis of these images. We're going to take a look at just one more sequence now after the event when the gas bottle gets fired. You can see that particles are flying all over the place. We really did kind of make a mess on the surface of this asteroid, but it's a good mess. It's the kind of mess we were hoping for. Lots of material has been mobilized, giving us additional confidence that we actually pushed material up into the sampler head. And just a little bit of the timeline here. We made contact. About 1 second went by. The gas bottle fired. The gas was blown down for about 5 seconds, which is as much time as we were hoping to get to collect that material. So the system seems to have performed nominally. The surface of Bennu behaved very well. And so everything that we can see from these initial images indicates sampling success. We still have some work to do. We're going to go through our entire procedure, including what we'll hear from Sandy later in the day about the additional activities for sample verification. So in case you can't tell, I'm pretty excited about all of this. This is great news. And I'm going to turn it over to Rich to talk about the spacecraft performance from here.
Thanks very much, Dante. Happy to be here. We're all super excited to be sharing all this information with you. And I'm going to try to set some context for the movie that Dante showed, with showing you exactly what happened during the last stages of TAG and orienting you with what our sample site Nightingale looked like. So let's begin with the animation. This is the final descent stages. This is the same perspective you see in the images. This is an animation, of course. So we'll transfer to a perspective that's near the surface, so you see just how rugged the terrain is here. And then at contact, you'll see the sample collection head make contact with the surface. Regolith gets disturbed, and then the nitrogen bottle gets fired, and more regolith get disturbed. The cutaway of the tag SAM, or the sample collection head, shows the airflow of the nitrogen and the back away maneuver from the surface. So that completes. That maneuver completed the sequence, and we're safely away from the surface right now. I'll turn now to orientation of the sample collection site Nightingale, and we'll show a graphic to describe that. So you see on the upper right is an image from our reconnaissance C. The resolution in that image is about 4 millimeters per pixel. The yellow circle in that image is the dimension of our sample collection head. So it gives you a sense of the rocks, the material that was under the collection head at the time of contact. And then the bottom right is just the snapshot of the sample collection head just before contact. On the left-hand side of this graphic is the Nightingale site. And annotated on that graphic is our estimated point of contact, which is less than a meter away from the center of the site. I'll emphasize that because we're over 320 million kilometers away from Earth at this point, and we touched this asteroid within a meter of where we intended to. So that's extraordinary, and a real credit to our team, our navigators, the folks here at Lockheed, and the science team, who all had to come together to enable that to happen, to allow the navigation system to work, as Administrator Bridenstine said, outperforming our requirements. Our initial requirements were to land within 25 meters of a specified site. We landed within a meter. So incredible there. And also the rugged terrain you saw from the perspective near the surface of the site. Extraordinarily rugged terrain. The sample site Nightingale is actually one of the smoother areas, but quite small compared to that 25-meter requirement. Now we'll talk a little bit about where the spacecraft is presently. We'll start an animation that begins with the backaway maneuver. You see the thrusters firing. This is a 40 centimeter per second maneuver, which may not sound like much, but you see the spacecraft going away quickly from Bennu and out of orbit. This graphic shows the orbit we left from, and then we're on a hyperbolic trajectory, safely drifting away from Bennu. We will actually arrest that drift away on Friday at about 80 kilometers distance from Bennu. So all the mess that Dante described that we made, we're safely away from all that debris field at the present moment. And I'm going to turn it over to my colleague Sandy Friend from Lockheed.
All right, thank you, Rich. I'm going to talk a little bit about the spacecraft performance yesterday and what is coming up. So the spacecraft performance was phenomenal all throughout the TAG event, performing just as planned. Natural feature tracking, matching all of its features as we slowly descended. You've heard and seen from the images that we made contact, fired the gas bottle just as planned, and we hope to have a lot of regolith captured in there before we backed away. We did start downlinking our TAG data yesterday. We were fortunate to maintain communication throughout the contact and our 40-bit telemetry. Last night we were able to go to a higher data rate and get down some of our recorded data, including that phenomenal set of images that Dante just showed. All of our spacecraft subsystems are reporting nominal performance at this time. We're not working any issues. We did see a number of additional bright objects in our star tracker, not unexpected, seeing what came off the surface of Bennu, and that has all now cleared. So coming up, we have a series of spacecraft activities that's going to help inform us on how much sample we've collected and give us a little more insight into the spacecraft subsystems. Our first event will actually happen tomorrow, and we've got an animation showing what sample imaging looks like. So we're able to articulate our arm and the tag SAM head over our SAM cam, which will take a series of images. We are hoping that we can see lots of sample entrained inside the sampler head. We'll also be able to see evidence of sample on those contact pads, any dust that may be on the arm or the sampler head. So that'll be the first activity to help us determine just how much sample we've collected. Then our second activity is our sample mass measurement, and we have a second animation showing that. We'll extend the arm and spin the spacecraft. Now we've done this activity before, so we've got a pre-tag, and this will be our post-tag. That way we can compare the moment of inertia, which will help us determine how much mass is actually in the sampler head. We do also have a spacecraft checkout planned early next week, where we'll get an opportunity to do some engineering checkouts of some of our redundant components as we continue to trend the spacecraft, which looks just absolutely amazing after what we put it through yesterday. I'm going to turn it back over to Nancy.
Okay, thank you, Sandy. We're now ready to take questions from the media by phone. Operator, please patch through our first question.
Thank you. We will now begin the question and answer session. If you would like to ask a question, please press star 1, unmute your phone, and record your name. Your name and your associated press is required to introduce your question. To withdraw your question, please press star 2. Again, to ask a question, please press star 1. The first question comes from Marsha Dunn from Associated Press. Your line is open.
Congratulations. I heard Mr. Bridenstine say that contact was actually 15 seconds, which is a little longer than anticipated. I guess that's a good thing, right? And when do you think might be the soonest that you can declare success and have at least a pretty good hunch that you got what you were going after? Thank you.
Great question. I'll tell you, the 15 seconds I got in open media reports, so I'll let probably the experts tell us exactly what they know occurred. If Dante, if you'd like to take that.
I think I'll let Sandy answer that. She's our spacecraft engineer and analyze the telemetry that gives us that information.
Yeah, so our preliminary analysis of the telemetry shows that we were in contact with the surface for about 6 seconds. And our collection time about 5 seconds. It takes just about a second after we make contact before that gas bottle is fired, which is that 1 second difference.
So I read an article and it said 15, so I guess I was wrong. Marsha, I apologize.
Oh, that's quite all right. And when do you think the soonest might be that you'll have, if not an exact measurement, a pretty good idea that you that you can that the pressure might be down?
Yeah, so we're continuing. Oh, go ahead.
I just was going to say, I'll defer.
Oh. Yeah, so we're continuing to analyze all the engineering data that we have on the ground so that we can better correlate all the data sets together and get an exact timeline of everything that happened here on the surface, how fast the bottle pressure went down, and all of that is being looked at very closely here as we look to analyze the sample we've collected. So hoping to have good solid timelines here in the next few days.
I think the sample mass measurement is planned for Saturday.
Yes.
That's when the spacecraft will execute that maneuver, and the team needs some time to analyze that information. And so, Sandy, remind me, when do we expect the final report from GN&C on that value?
Yes, we are expecting a final sample mass measurement report on Monday.
Thank you.
Operator, we're ready for the next question.
Thank you. Tariq Malik of Space.com, your line is open.
Hello. Thank you so much for the update here, and congratulations, it appears, so far on the sampling. My question is for Dante. I'm just curious. It's been a long road reaching Bennu with Osiris-Rex, and very unexpected circumstances to try to actually collect samples of the asteroid last night. And I'm wondering kind of what you and the team are feeling or were feeling when you saw those images come down after, making lots of precautions for, the ongoing pandemic or, every other challenging situation that we're facing right now. I'm just curious kind of what that tone was like when you saw those images there?
Of course, that's a great question. So we stayed here at the MSA at Lockheed Martin fairly late last night. I stuck around to get to the point where we made the high gain antenna contact with the spacecraft, and we started to get the initial telemetry back down. And we actually had a spacecraft status meeting about 9:30 p.m. here, local Denver time. I got back to my apartment here in Denver around 11 o'clock last night, and I couldn't sleep. As you can imagine, I knew we were expecting those images around 2 a.m., so I got on to the chat. We have a chat feature with our science team, and the images get processed through the Science Processing and Operations Center in Tucson, Arizona. So our imaging scientists at U of A were busy downloading and analyzing the images, and the science team was analyzing them in real time through the chat feature. And we were producing the animated GIFs, looking at various aspects and timing in the sequences. And as you can imagine, the chat was filled with emojis and wows and all kinds of celebratory remarks. Science never sleeps in these kinds of conditions, so we immediately started assessing how far the TAG-SAM head penetrated into the surface. Overall, the mood was jubilant because everything looked better than we expected. And I could say the best piece of information we got was that TAG-SAM head looks like it pushed down into the asteroid surface. With all the laboratory testing that the team at Lockheed Martin did here to assess TAG-SAM performance, some of the best test results occurred when TAG-SAM gets down underneath the surface just a little bit and is able to fire the nitrogen gas with regolith all around it. So I know we're going to hear at another event later today from our TAG-SAM scientist, Bo Bierhaus, so you can look forward to that. I know he is literally over the asteroid at this point with excitement about how his device has performed, and that spread throughout the entire science team. The only thing I'm looking forward to is maybe being able to sleep tonight knowing that we had a job really well done.
Thank you, Dante. Operator, next question.
Thank you. Stephen Clark of Space Flight Now, your line is open.
Hi, congratulations on the success. My question is for Dante. Are you at any point in the next few days or few weeks expecting to get any images inside the TAG-SAM to see maybe an image of the sample that you collected? And I was wondering also if you have any estimate of the error bars that you'll have on your mass estimate from the spin maneuver this weekend. Thanks.
Yeah, thank you, Stephen. Absolutely. So I think the next major flight activity for the spacecraft is using the SAMCAM to image the TAG-SAM head. Sandy showed an animation of what that sequence looks like just a little bit earlier. We will be able to look at the base plate. We'll be able to look at those contact pads. Based on what I've seen so far with the asteroid surface crushing underneath the TAG-SAM head, I'm anticipating that we see contact pads coated in dark black asteroid regolith. But of course we need those images down to verify that. We hope to be able to see inside the TAG-SAM head, but that's not guaranteed. For one thing, the TAG-SAM head may be so full of regolith that no light is able to penetrate inside that. I'm going to take that as a win. But it does require just the right lighting conditions for us to see inside that TAG-SAM head, and we don't require that to take place. But those images will be acquired tomorrow, downlinked over the next day or so, and obviously we'll be analyzing those intently. Remind me what the second part of your question was?
Yeah, just how precise is this moment of inertia measurement going to be in terms of estimating how much mass, how much sample you collected?
Thank you. So the mission requirement is to bring back 60 grams of regolith. And we have done a lot of work with this team to determine what the precision on that measurement is. And in fact, we rehearsed it during the checkpoint rehearsal and the match point rehearsal. Right now, we're carrying a 3 sigma uncertainty of about 20 grams on that measurement. So we've actually worked through this with our stakeholders at NASA headquarters, and 80 grams is kind of the magic number. If we see SMM coming in at 80 grams or higher, we have a 90% confidence of having collected 60 grams of regolith. So that's a key number that I'm looking for. If it's below that, it's a conversation that we have with the team, with NASA headquarters, Dr. Zurbuchen, to decide what do we think the best path forward is. But 20 gram 3 sigma is the number that we have agreed to with the agency.
Thank you. Operator, next question.
Craig Smith of KUN Tuscan, your line is open.
Thank you. A question for Dante. How is it decided just which organizations get which share of the collected material? What share do you expect University of Arizona to get? And please give us an idea of, I guess, the researchers who are lined up to get a look at that material.
Thanks, Craig. Great to hear from you. So first, the sample belongs to NASA and really to the American taxpayers. So the only transfer of sample that's been authorized is that 4% goes to the Canadian Space Agency. That's by mass. And then 0.5% goes to the Japanese Space Agency to reciprocate for their contributions to the success of this mission. The science team, which is what I lead, will be allocated 25% of the return mass and also 25% of the contact pads for our scientific analysis. But in all cases, that material still belongs to the agency and is under the control of NASA. And it's allocated to me and to the science team through what's called a loan agreement. But all that aside, we're basically planning right now on analyzing 25% of the return mass. And a lot of my activity lately has been in writing my sample analysis plan. And this has been really exciting to get to this stage in the program where we can lay out in detail the different analysts that will be looking at the material. Of course, the University of Arizona will be a central organization in the analysis of the return material. We've got new laboratories that we've installed over the last couple of years, a new instrument being developed right now that we're really looking forward to analyzing that material with. But the science team really spans the entire globe. We've got key organizations in the United States like NASA's Goddard Space Flight Center, Johnson Space Center that are going to play central roles in the sample analysis program. And then we've got team members in Canada, in Japan, and Australia, throughout Europe that are going to be involved in the program as well. And we'll be able to talk about that and roll that plan out over the next year or so as we finalize the details on that. But I can tell you, based on what I've seen today, we're looking at hopefully a lot of material and a lot of great science coming out of the sample analysis phase of Osiris-Rex.
Great.
Great. Thank you. Congratulations.
Operator, next question.
Leo Enright of Irish TV, your line is open.
Thanks very much for doing this, and congratulations. A couple of questions. One for Rich Burns. You mentioned the possibility of maybe less of a sample than you had hoped for. Now, I realize this is unlikely, but if you found that you had less of a sample than you expected, is there a plan B? Can you go back, or is that it? And also for Dr. Loretta, can you talk a little bit about the rocks that we saw? You mentioned that the rocks seem to fragment very easily. What can you say about the nature of these rocks, and whether, for instance, if I picked one up, would I be able to crumble it in my fingers?
Thanks very much for that question. It's a great one. If we for some reason decided not to stow this sample, if we determined the mass was not sufficient, that we wanted to go back, we can in fact go back. We have 3 nitrogen bottles, which allows us to touch the surface 3 times. Of course, we've disturbed, as you saw in the animation, or not the animation, but the images that Dante showed, we've disturbed the surface of Nightingale in a radical way. So we won't be going back to Nightingale, at least for our second attempt. We would go to our backup site, which is called Osprey, which is a near equatorial site, and we're prepared to do that in the mid-January timeframe. I'll turn it over to Dante for to answer the second question.
Yeah, the rocks on the asteroid surface have turned out to be fascinating scientifically, and the team has done an amazing job processing all of the remote sensing data that we've acquired starting in late 2018 and throughout 2019. I can answer the question that, first of all, the surface seems to be dominated by 2 distinct rock types. We see a very dark, kind of hummocky rock, which looks like the one that we crushed underneath it. And from recent analysis using the thermal data, how the rock heats up and cools off, we actually inferred that these rocks might be very weak compared to what we're used to dealing with here on Earth. And most exciting, I think, for me as a sample scientist, very weak compared to the meteorites that are currently in our collections here on Earth. So I think what we've seen is that our meteorites are possibly a biased sample, that they're only the most sturdy and strong material that survives passage through the Earth's atmosphere. And it looks like the material that dominates the surface of Bennu might be much more fragile and friable. And with this interaction of TAG-SAM with the asteroid surface, that seems to be playing out. I can tell you the science team is already excited about the possibility of getting a direct strength measurement through detailed analysis of this image sequence, especially these two images right before and right after contact. The second kind of rock that we've seen on Bennu is a little brighter. It tends to be shot through with bright white veins or white inclusions that we've identified as a mineral carbonate. This is a mineral people are probably familiar with. It forms a kind of white crud around your faucets and sinks if you live in an area with hard water. It's basically an evaporite, and those rocks seem to be a little stronger, probably because of that material that has cemented them together. We do see maybe some hints that there was some of that brighter material, smaller fragments of it, underneath the TAG-SAM head, but the team is going in for detailed analysis to determine if that's in fact the case. And then I'll just add, mineralogically, we've done a pretty good job understanding what these rocks are made out of. They're definitely dominated by hydrated minerals, that is, clays that have water contained in their crystal structure. That's very exciting scientifically. We've also seen an iron oxide called magnetite, abundant organic material, particularly carbon-hydrogen bonded material, which is really what this mission is all about, bringing back home, and then that carbonate material that I mentioned earlier.
Thank you. Operator, next question.
Nova PBS, your line is open.
Hi, everyone. Firstly, congratulations. This is just super exciting, and I know that we're all, to use your point earlier, over the asteroid for all of you guys. And if I'm wondering, from the images that you have currently, I know during Monday's press conferences there was a lot of conversation about diversity in regard to the size of the sample pieces as well as the material and everything. So is there any clue from the images that you have currently that we have a good diversity of really small pieces and maybe pieces closer to that 2-centimeter mark and maybe of different types of material as well? I guess that's for Dante or really anyone who can answer.
Yeah, I'll take that. I can say just within the past hour or so, I got the analysis from my image processing team about the exact location where we think the TAG-SAM head made contact. So I haven't had time to process that information. I know that team is busy analyzing that. But from that quick look assessment, it does appear that we made contact with an area that had already been mapped out and verified to contain abundant sampleable material. Rich mentioned the imaging resolution during the Recon-C characterization of Nightingale, where we got down to that 4 millimeter per pixel scale. So that this region does look really sampleable, lots of small particles, and then the fact that the material just crushed underneath the TAG-SAM is just going to add more smaller particles for us to collect. But I don't want to answer the question just yet about the diversity of the rock types there, because the team is still processing that right up to the beginning of this media briefing.
Operator, next question.
Thank you. Let's see. And Ryan of Arizona Republic, your line is open.
Thank you. I wondered if you could explain a little bit more about how you will measure how much sample you've collected besides the possibility of images.
Yeah, so we've got a sample mass measurement activity. So we've been practicing this, as I think Dante or Rich mentioned, around our checkpoint and our match point burns, or activities where we can extend the arm and rotate the spacecraft, and we can measure the moment of inertia. And by doing that before TAG and doing that same activity after TAG, we can take the difference in those measurements to estimate the mass. So we did perform our pre-tag sample mass measurement activity about 10 days ago, and we'll do our post-tag one this Saturday, and we'll be able to take those two measurements and look at the difference of them to get that estimate of how much mass we believe is inside of the tag SAM head.
Operator, next question.
Thank you. Chuck Field of Your Space Journey, your line is open.
Thank you, everyone, for taking my call, and just congratulations to the entire team. I'm just wondering, what are the reasons for waiting until January for a second collection attempt? And if a third attempt is required, have you determined when will that take place and at which site?
So, yeah, great question. The reason that we would do a second attempt at Osprey in January, as you saw, we're backing away from the asteroid right now. And I mentioned that we'd be about 80 kilometers when we make a maneuver to arrest that drift away on Friday. That will put us on a trajectory that goes to a waypoint where we can re-enter orbit. You see the orbit in that animation that was just shown is a tenuous trick to get into. Bennu is only 500 meters in diameter, so its gravity field is extraordinarily weak. Just getting into orbit takes weeks of maneuvering to get there, and we also have to phase the orbit appropriately so we depart for the next sample collection attempt at the right latitude. All that takes weeks of planning and preparation. We also have to prepare the spacecraft to tag at a different site, which involves generating the spacecraft commands, testing them, and so forth. So that runs out the timeline to January. And then the third sample attempt would be to be determined date, most likely in March, when we'd be attempting a third attempt. But it largely depends on what happens at Osprey. If we were to go to Osprey in January and wave off, abort for some reason, and not touch the surface and not disturb Osprey, as we've seen the dramatic disturbance of Nightingale, we go back to Osprey. If we did disturb Osprey, that's a contingency that we would have to either perform more reconnaissance over one of the two, Nightingale or Osprey, or follow some other path. And the reason I'm saying that is we use optical navigation to get down to the surface. So much as you're driving to some location in your local town and you know where you are, where a gas station is or a supermarket, the spacecraft knows where it is by features on the surface. So groups of rocks that cast shadows or just clusters of rocks that have distinctive features are recognized by the spacecraft in its imagery as it descends, and it knows where to go. It knows to take the right turn at the supermarket to get to the center of the site. So once we disturb all those features, that means we're going to need to take more images and build a new set of feature catalogs to teach the spacecraft where the grocery store is.
Great. Thank you, Rich. Operator, next question, please.
Joshua Ortega of Quartet News, your line is open.
Thank you for having me, and congratulations to everybody involved in this mission. What was one of the biggest discoveries that you made in making contact with the asteroid Bennu that you didn't expect? And my second question is, what is the future applicability for future projects with some of the technology utilized on the spacecraft?
I guess I'll take the discovery question. I could say we've had the data down for just a little over 13 hours, so the discoveries are still to come. What I was looking at this morning, 2 o'clock here, Denver time, after being up through a very exciting event, was how does it look in terms of getting the sample? So the science is something that we're going to think of down the road a little bit, but I can tell you that I was hopeful that the surface was going to be soft and crushable, and that was confirmed by our contact with the tag SAM and analysis of the images that we've seen here so far. So that is really good news. So I'm pretty focused on sampling success right now. I will tell you the science team is busy in a couple of different areas. They are working through a detailed analysis of this entire image sequence, along with additional data from the spacecraft guidance, navigation, and control team about exactly what happened when the spacecraft was in contact for those 6 seconds. That'll tell us a lot about TAGSAM performance, and there's also follow-on science that we'll be able to do with that information. But right now, I would say the big discovery is that it looked really sampleable, that the TAGSAM head pushed into the surface, and that it was in a very good position when that gas fired to collect a lot of material. So we still have all the confirmation activities that Sandy walked us through earlier in the briefing to verify all of that. But the trend right now is that we have sample and that we were successful here based on analysis of this image, this set of images.
Yeah, I'd love to speak to the second part of that question if possible. Yeah, so the question was what technologies on board the spacecraft can enable future missions, and I think one of the most amazing technologies is the optical navigation system I talked about, what we call natural feature tracking. And it has actually an amazing story. The spacecraft was originally designed to use a LiDAR to measure the altitude to the surface as its primary sensor to do the navigation to the surface. But natural feature tracking or optical navigation was added around the critical design review time period in order to have a backup solution. And as I mentioned, what it does is recognize features on the surface of the asteroid and then update its own sense of its position so it knows where to go in the future. Now, this technology being added late in the game was done by our colleagues at Lockheed Martin, and it was an amazing accomplishment, amazing engineering accomplishment, and one of the most amazing performances of the system yesterday was just how well that system performed relative to our simulations of it. Optical navigation systems are notorious for not performing as expected, and this one performed exactly as expected and allowed us to hit that center of the target within a meter. So our colleagues at Lockheed Martin deserve a lot of credit for that. And how that gets applied in the future is it will allow for autonomous navigation for other deep space missions to small bodies or not, for landing or navigation around hazardous or non-hazardous environments. So I don't know if, Sandy, do you want to follow on to that at all?
Yeah, definitely. I would for sure have pointed out natural feature tracking as a capability that I can see useful in the future. I'll also point out that TAGSAM is new technology flying on board the spacecraft, and you can see that going forward for future sample collection, sample return missions.
And one more quick question for the NASA representatives. What is this? Is this the first time working with the University of Arizona, and what does this say about the school and future projects with the school as well?
It's Thomas here, head of science. No, this is not the first time. I think of the University of Arizona, and it's partner university up the street, so to say, Arizona State, to really be kind of meccas of planetary science and exploration. The University of Arizona has had the principal investigator of multiple missions and continues to compete very well in many different areas. And really, especially in planetary science, the University of Arizona is one of the top leaders in the whole country.
What did you say about Arizona State University as well?
Arizona State University, frankly, is if you just lined up kind of the top universities in planetary science, both the University of Arizona and Arizona State rank in the top part of such a ranking list. So Arizona State also, at this moment in time, for example, has a principal investigator of a discovery mission called Psyche. There's instruments that are being built there for other missions. So also Arizona State is a really critical partner for NASA in this and also other disciplines.
Thank you. Thank you very much for your time.
Thank you. Operator, next question.
Mark says, Magazine. Your line is open.
Hi, thanks very much for taking my question, and congratulations to everyone. I just had a couple of questions on the series of images that was released and the really impressive rubble cloud that this kicked up. Just wondering if you're able to glean anything scientifically about the surface material from the dynamics of that cloud and the rocks and particles that make it up. And then obviously you expect it to make a mess, but what kind of safeguards or system checks are in place to make sure that the craft wasn't damaged by that? And then finally, I was just curious, what is the time step between those images? So what's the effective frame rate of that video?
So I'll answer the imaging questions, and I'll hand it over to Sandy for the safety assessment of the spacecraft. So right to your final question, those images are about 1.25 seconds apart. So the first version I showed, which was the larger image sequence, was sped up by quite a bit relative to that frame rate. In terms of the debris cloud, absolutely. It actually is kind of impressive. The fragments that we see flying around, there's some pretty large particles. One of the things the science team has already started doing is tracking the trajectories of the particles. As we see them mobilizing across the images here. They're going by pretty fast right now, but obviously we're slowing those down, identifying individual particles. There's other images, too, that we collected with a different camera called the NavCam, the one that was used for the natural feature tracking. I was getting a quick look at those right before the media conference. Those are fresh off the spacecraft, so we're still processing those and analyzing those, and those will be released a little later on this week. But those give us a wider field of view as well, so we're kind of getting this great point of view of the SAMCAM contacting the asteroid surface and all the particle debris that we see. And then we have the NavCam 2, which is off-pointed a little bit in a wider field of view, so they're going to be a nice image pair. And I think the final thing to point out is that the initial ejection of particles actually comes from the TAGSAM gas as it was blown down through that sample collector head. But you got to remember, we were only in contact with that asteroid for 6 seconds. After that point, the back-away thrusters fired, and those kicked up a second set of cloud and debris. So we're still disentangling that whole history. What was liberated by TAGSAM, what was kicked up by the back-away thrusters, and the NavCam images are pretty fresh right now on the ground. So we got a quick look at those. They're very impressive, just to get everybody excited, but we're not ready to release those because we haven't really had a chance to process them ourselves quite yet. And I'll hand it over to Sandy about the safety assessment.
Yeah, so the spacecraft was designed for this. We knew when we made contact that we were going to stir up a lot of regolith. There was a large backscatter study done during development to make sure that we would keep the spacecraft safe. Now, just by monitoring this spacecraft over the last, close to 24 hours now, we've been able to see a number of components, and we're trending, as our subsystems do throughout, making sure that things are going as planned, and they're not seeing any changes in their measurements. Now, on next week, early next week, I believe Monday, we'll be doing a spacecraft checkout, where we'll get a chance to take some star camera images on both of our primary tracker and our redundant tracker, and we'll get to do some other engineering activities to better inform us if we've had any sort of degradation on the vehicle.
Great. Next question.
Lisa Grossman of Science News, your line is open.
Hi, thanks for taking my question. I was wondering if you knew if any of the regolith that got disturbed, any of the stuff that got tossed up into space around Bennu would end up at Earth, and if maybe you just created a new meteor shower.
Hi, Lisa. I'll answer that one. I think you read my mind. I certainly have been thinking about that. We have thought about that, as I mentioned yesterday, and we've talked about for quite a while on the mission. Bennu is already kicking particles off the surface, and one of the things that we are doing is monitoring for a meteor shower, which would occur in the southern hemisphere in the third week of September, which is when Bennu's orbit crosses that of the Earth's orbit. We actually had data that we just recently received from that meteor campaign, and we're still processing that to see there's maybe a small signal, but maybe not, of natural Bennu meteors. So that idea is already in place. That kind of study is something that we're already pursuing. So I'm going to go back to that team that's responsible for that investigation with your exact question. I haven't had a chance to ask them that. I didn't dare to hope that we would kick up as much debris as we're seeing here. So I'm not sure, but it's definitely a question I've asked myself, and we've got team members who are thinking about that based on Bennu's natural particle ejection events. So it is a natural line of inquiry, but we just need some time to push through this very exciting operational phase of the program and start to think about some of the long-term science implications. We do have a phenomenal scientific data set. TAG was a great science experiment, and so there's going to be a lot of work that comes out of it, but we need time to get the data down, to get it calibrated, processed, and to just spend some time thinking about it without all these critical operational decisions in front of us like we have over the next couple of weeks.
Okay. Next question, operator.
Stephen Clark, Flight Now, your line is open.
Hi, thanks for taking another question. Dante, the material that we see in the imagery that was disturbed and kicked up with the TAG event, any estimate yet on how big some of those particles might be? They look kind of small, but it's hard to tell from the scale. And also, if you did collect the required sample of 60 plus grams, what is the flight plan for Osiris-Rex over the next few months, and do you have a date for departure for Earth? Thanks.
Yeah, great question, Stephen. Can we bring up the third set of images that I was showing here where we were looking at some of the debris and maybe slow it down a little bit? I know we talked about that. So just remember, for scale, we're looking at this TAG SAM head, which is 30 centimeters in diameter. This is the full-scale model here. So you can get a sense, you know, the spacecraft's only a little over 2 meters away, or 6 feet away, so not much farther than my span here. So you can actually kind of estimate the particles. You know, so we're looking at things, you know, that's probably on the order of centimeters to several centimeters. And then we've got this guy here. This is a pretty amazing looking particle. So if it was to scale with the TAG SAM head, it would be on the order of 15 centimeters. It's probably a little closer in our field of view, so it's going to be a little smaller than that. But this is the biggest one that I've seen so far in my assessment of the data. Of course, the team is going through with much more careful analysis. But I'm guessing this is multiple centimeters, maybe up to 10 centimeters across here. And this guy kind of comes shooting off from the right side of the field of view and moves over off the image to the left. So there's certainly a lot of work to do to really get a sense of how far away, what's the depth of field of view of the image that we're seeing here, and to do some real precise measurements of the sizes of these particles. But this one alone shows me we picked up some things that are pretty big. But for the most part, we're looking at centimeter, sub-centimeter scale particles just from a quick look assessment. But there's a lot more detailed analysis to go. This is all preliminary, and the image processing team at the University of Arizona is busy, as we speak, answering that exact question right now. And then I think over to Rich for the departure date and the return cruise.
Right, so if we stow the sample, we'll be doing so in the first week of November. And we'll follow continue to drift away from the asteroid after we make that maneuver on Friday, rather than attempting to reinsert into orbit. Our departure window opens in March. That's when the orbital mechanics say it's fuel efficient to get back to Earth, and our designated date in September of 2023. We'll depart the asteroid in early March at the opening of that window.
Okay, we have time for one final question. Operator, please patch it through. Operator, do we have another question?
I do apologize for that technical issue. Michael Greshko with National Geographic, your line is now open.
Hi, thank you so much, and congratulations to the team. I had a question about sort of the aftermath of this tag. What are the plans, if any, to do any sort of remote sensing on Nightingale site to sort of see the hole you all left? And then more generally for the team itself, I mean, this moment has sort of captured the world's attention. Anything at this time you want to say to, you know, people around the world who are watching this and sort of taking this in along with you?
Sure, I'll answer that. It's a tough question, Michael, because there was a lot of interest from the science team on more data, more characterization of Bennu after the sampling attempt. But we gathered together as a management team and we evaluated that exact question very thoroughly. And we agreed unanimously that this mission is about safe return of this sample. And we do not want to do anything to put that sample at risk. So the plan right now is we're going to go through these verification activities on the flight system. We're going to check out the state of the vehicle. If everything looks positive and we meet with Thomas on October 30th and make that decision to stow, that is the end of the science campaign at Bennu. We are then solely focused on the return cruise. And quite honestly, the real scientific payoff, which this mission is designed to do, is that sample return and the sample science. And we'll be putting our focus and our resources into that. It wasn't an easy decision, guarantee you. It was tough, especially the scientist in me always keeps asking those questions, but it's the right decision to maintain that focus on the level 1 requirement. Because I can tell you, right before we kicked off the tag activity, I went through all of our publications and all of our data, and I mapped them to the level 1 requirements of the mission, which is what I agreed to with Thomas and Lori that this program would deliver. And we have met, and in most cases vastly exceeded, all of the science requirements associated with the remote sensing campaign of Bennu. So all we have left to do to deliver on our promise to the agency is get that sample safely back to the Earth, get it into our laboratories, and answer the fundamental questions about the formation of our solar system and why Earth is a habitable world. And then you gave me a chance to promote a message, and I'll just say, Osiris-Rex, in my opinion, is the culmination of human activity as a species. We built this mission for peaceful purposes, out of curiosity and our desire for knowledge. It's a team that comes from a variety of backgrounds and viewpoints, but none of that matters because we work together, united in a common vision and a common goal. And when we do that, we achieve amazing things. And so I told the team, I know we focus so much on the details and the technical implementation of this program, but we serve as a model for what we can do as human beings when we unite in a common vision. When we're united, we're strong, and when we're divided, we're weak. And so I hope that message of unity and common purpose, and that we're all in this together, right? We've got this precious planet Earth that we're the stewards of, that we're responsible for. And when we come together and unite, we achieve amazing things.
Could I follow on to that as well, please? Yeah, I think one additional thing to add on to that, beautifully put, words from Dante, is, we're hoping to serve for an inspiration for future scientists and engineers. This mission is as much fun as you can have and get paid to do, right? So I had one of our instrument scientists was examining the images from our navigation cameras as it came down this morning. He said, his subject line, his email he sent to me, the image was, "This is so cool," right? And it is. And what he finished his email with was, "I love this job." So we're hoping that, there's 5, 6, 10-year-olds out there that get inspired by this mission, the amazing achievements of this mission, and it's the people, the engineers and the scientists on this mission that made it happen. So we need our future generations to be inspired by this, and that's what we're hoping to do. And I think the other thing is, Dante mentioned the sample allocation. A large fraction of the sample is going to be reserved for study of future generations. So we're hoping that future sample scientists are inspired by this. And, kids at home today could be the ones studying this sample in 10 or 20 or 30 years and make new discoveries that aren't even possible with today's technology. So, thank you.
Well, that was a great way to wrap the show up. And as your engineer said, the images, they are cool. So before we close, we'd just like to invite everyone to tune in to the NASA Science Live that's going to follow this press briefing at 6:15. So go on over to nasa.gov/OsirisRex, where you'll see a presentation from various Osiris-Rex scientists. They'll talk a little bit more about the images and about the overall Osiris-Rex mission. I just want to say congratulations to the team. Go Osiris-Rex. and thank you for tuning in.